Okay. It is my pleasure to introduce Ning Xie, an incoming assistant professor at the University of Toronto. Her work is, and also currently a researcher at DeepMind. Her work on functional programming types and related things speaks for itself. She has 2 distinguished papers, one at Popple, one PLDI. And without further ado, let's hear her speak about machine learning programming.
Thank you. Yeah, thank you for the very kind introduction. It's a pleasure to be here. So for this talk, I will present my recent work on language design for machine learning programming, in particular on a specific kind of machine learning, which we call choice-based learning. And I will start this talk by a brief overview of the machine learning field and then explain what I mean by choice-based learning. Then I would present our language design for choice-based learning, which is implemented by combining 2 functional paradigms, algebraic effects and handlers, and the selection monad. Finally, we have a prototype implementation of our design as a Haskell library, and I will describe the library at a high level and present some learning examples towards the end of this talk. And by presenting this talk, I hope to offer some perspectives on how functional programming can be applied to machine learning programming. And as mentioned, while I work for the University of Toronto, I'm also a member of Google DeepMind, and this is joint work with my colleague, Gordon Plotkin, at Google DeepMind. So generally speaking, machine learning is a collection of algorithms and techniques that allow computers to learn from and make predictions on data. As an illustration, these slides include the 3 applications of machine learning in the past decade. The first is for the game of Go. It refers to AlphaGo, which defeated a Go world champion, and it is now arguably one of the strongest Go players in history. And the figure in the middle is about image generation. Here you can see a puppy in a nest emerging from a cracked egg. Finally, the one on the right refers to the recent development of AlphaDev that discovered fasting sorting algorithms, which have been integrated into the LLVM standard C++ sort algorithm. As you can see, machine learning has found applications in various fields, and it can sometimes be creative in discovering new knowledge. At the same time, machine learning is also an extremely hot topic in academia. This figure shows the number of AI publications through years from 2010 to 2021. And the numbers are in thousands. For example, in 2021, we have more than 42,000 papers in machine learning, which means there are more than 100 papers per day. And of course, there are also other aspects related to machine learning in other AI fields. So the success of machine learning can be attributed to the advances of machine learning algorithms, the large amount of data and devices that are available nowadays, as well as the development of machine learning frameworks and technologies, especially with frameworks such as TensorFlow, PyTorch, and more recently, JAX. And perhaps surprisingly, but also quite naturally, machine learning frameworks, just like any other programming language frameworks, has close relation to the programming language community. For example, Martin Abadi gave a keynote about TensorFlow at ICFP' 2016, where he offered some perspectives on how TensorFlow and machine learning in general are related to functional programming. And Matthew Johnson, as well as Rolf Foistig, they presented the JAX, the basic building blocks at various PL events, including a Rebase, which was co-located with Splash 2020, and Laffy, which was co-located with Popple 2022. And you can see from the title, JAX accelerated machine learning research via composable function transformations. It already sounds very relevant to functional programming. And of course, except the part about Python. And both Martin and Matt and Roy are all my colleagues at Google DeepMind. But I mentioned these 2 talks about TensorFlow and JAX, but not any talk about PyTorch, not because they are my colleagues at Google DeepMind, but because I'm not aware of any PL-ish talk for PyTorch. And if anybody knows about such a talk, please let me know. On the other hand, those existing frameworks often rely on the implementation language, such as Python, or the domain-specific language for specific paradigms. And while there are also existing studies of programming paradigms for learning, they have focused on specific models, such as probabilistic programming for probabilistic models, or differentiable programming and automatic differentiation. So the question we ask here is, can we come up with a general language design that is good for machine learning programming? This talk presents a PL for ML study, which is one attempt in this direction. This slide summarizes the key idea of this talk, where I will show that a specific kind of learning, what we call choice-based learning, where choices are driven by optimizations, can be implemented by combining two paradigms, algebraic effects and handlers, and the selection monad. The hope is that by presenting this talk, I can offer some perspectives on the connection between functional programming and machine learning programming. And also in the second half of the talk, I will present some learning examples written using a Haskell library we developed. So in the rest of the talk, I will start with an illustrative learning example to demonstrate our key design. And then I will briefly review algebraic effects and handlers and the selection monad and show how these two can be combined for choice-based learning. And finally, I will discuss our Haskell implementation with various learning examples, and those examples demonstrate the expressiveness of our design, where different effects and handlers can be nested and composed for different choices. We start with an illustrative learning example. First, as I mentioned before, we focus on a specific kind of learning, which we call choice-based learning. And this includes decision-making models that describe systems in terms of choices and their resulting feedback as losses or delay rewards, such as the Markov decision process, or MDP for short. A Markov decision process comes with a set of states and a set of actions with probabilities that an action in a state can lead to a new state with an immediate reward. And this slide shows one example, one basic example I just made up. So we begin with a start state, and with 100% possibilities, let me see if I can open the laser somewhere. Okay, I gave up. So we begin with the start state, and with 100 possibilities, you will come to this talk, for which you will get a reward of 1, and hopefully you will learn something new from this talk. But during this talk, there are 40% possibilities that you will be starting looking at Twitter. And for that, you will receive a reward of -1, and once you do that, there are 90% possibilities that you will be staying at Twitter. And from this talk, there are also 50% possibilities that you will stay here for the next talk, and there are 10% possibilities that you will go to the hallway, get a cup of coffee, and network with people. Attending talks can make you tired, so the rewards of attending the following talks are decreasing. But there is a 1% chance in the end that you might get inspired and come up with a new research idea, and for which you will receive a reward of 100. And this example also demonstrates the challenge in training machine learning models for Markov decision process, which is the tension between the immediate reward you will receive by getting a cup of coffee and the long-term reward you may receive in the end if you are willing to receive some negative rewards along the way. And the example on the right of the slides is about gradient descent. In this setting, the model comes with a set of parameters and an overall loss function. And the goal is to find the best configurations of the parameters to minimize the loss function. And at each training step, we will choose new parameters at the opposite direction of their derivatives and get a new result as loss. So as you can see, the idea of choice-based learning can support different machine learning models. while we do not claim to support all different kinds of machine learning models, we believe the examples we support have already made our design interesting for further investigation. And for now, I will use gradient descent as an example to demonstrate our design, and we will see more examples later in the talk. To demonstrate the design, let's look at a simple training algorithm for linear regression with only one variable. That is, we are given a data set of xy points, and our goal is to find a weight W and a bias B such that this linear function f models the relation between x and y. We have a simple training algorithm on the right, which iterates all training examples. So we are given some initial parameters, and while not done, we are going to pick one training example, x and y, and compute y prime using the current parameters w and b, and we compare y prime to the actual y to calculate the loss. And according to the difference between y prime and y, we can choose new parameters for w and b. And a commonly used loss is the least square one that is shown on this slide. But on this slide, I have not yet shown how to actually reduce the loss, which we will discuss later. But first, I want to rewrite this example to be choice-based learning. Specifically, in this example, when we choose a new parameter, w and y, it's going to affect the loss we calculate in the next iteration. But to make the relation between parameters and their resulting losses more explicit, we can move these new parameters to be above the loss. So each choice will affect its own loss within one iteration. Now the question is, how do we actually choose the new parameters? To actually find the best weight and bias, we wish to apply gradient descent, which is a commonly used optimization algorithm. Gradient descent minimizes the loss function by, at each step, first computing the derivatives of the loss with respect to the current parameters, and then choose the new parameters in the opposite direction of the derivatives. For example, here we update the new parameters to be the current parameters minus 0.1 times the gradients. So just to briefly recap what I have talked so far, we have seen a training algorithm for linear regression and optimization algorithm using gradient descent. And you will observe something interesting when you put these two parts side by side, as you will notice that they are both about choices and losses. Specifically, the training algorithm knows about its training model and the loss associated with each choice, but it does not know how to make decisions. At the same time, the optimization algorithm knows how to choose new parameters, which is not specific to any training model. And based on this observation, we propose the key design of our system, which is to use algebraic effects and handlers for choice-based learning, where the training algorithm is an effect for computation using choose and loss operations, and the optimization algorithm is implemented as an effect handler for the choose operation that makes use of losses. More concretely, effects and handlers give a modular programming interface for choices made by effect operations, so that we can easily combine and compose multiple effects and handlers. And we will also make use of the selection monad, which enables handlers to apply optimization techniques based on losses. So this slide summarizes the key idea of our work. And in the next part of the talk, I will briefly review the concepts of effects and handlers and the selection monad, and show you how they can be combined for choice-based learning, in particular for this linear regression example. So, algebraic effects and handlers and the selection monad. We start with algebraic effects and handlers. People who attended yesterday's Haskell keynote by Nick might find the term already familiar, but in any case, let's review the basics of effect handlers. Algebraic effects and handlers provide a modular and flexible way to support structured control flow abstractions, and have been implemented in languages like Coca or Multiple OCaml, which has been integrated into the OCaml compiler. And we also had an ICFP keynote where the speaker talked about the development of effect handlers for WebAssembly. Essentially, algebraic effects and handlers achieve modularity by separating syntax, which is defined by user-provided effect operations, and then semantics, which is given by handlers. Because of this separation, effect handlers can achieve modularity by easily composing multiple effects and handlers. There are two key constructs of effect handlers, handler and perform, as shown in this figure for demonstration. Here, we consider each row as one evaluation frame in the evaluation stack, which is evaluated bottom up. And the part in blue denotes the scope of this handler. When the program performs an operation, in this case op, with an operation argument v, the program does not yet know the semantics associated with this operation. Instead, it must yield up to find a handler for this operation. There can be multiple handlers in the evaluation stack, and there can be handlers for different operations, but the program will always find the innermost handler for the corresponding operation. Then the program on the left will evaluate to the program on the right, where the expression E is what's there in the handler definition, but with X substituted by the operation argument V, and K being the continuation, capturing where the handler, starting from where the operation is performed to where the handler is found. And inside this expression E, the program can resume the original computation by calling K. Or it can choose to not call K at all or call K multiple times, as we will see later in examples. So let's go through some examples. Since this is a talk at the Haskell Symposium, the rule is that all examples must be written in Haskell. This slide shows one algebraic effect interface in Haskell developed by Dan and myself 2 years ago at the Haskell Symposium 2021. The effect for programs have a monadic interface in F, where this E keeps track of the effects. And an effect for program where all the effects have been handled can be run by calling this runF function. An operation has a data type declaration, and the two key constructs, as I have mentioned before, are perform and handler. Since some of the type variables here are really just there for polymorphism, to better illustrate the interface, let's highlight some key aspects of these type signatures. First, an operation has an input type A and output type B. For simplicity, we will always omit the other type variables in the rest of the talk. The perform function essentially takes an argument corresponding to an operation from A to B, and then an argument of type A, and returns an effect for program in the F monad with return type B. The type class constraint in perform says that the effect E in the return type must contain H, where H is hidden somewhere in the type signature. As an example, H can be the state effect, which has two operations, get and set. And whenever you use get or set, the monad will make sure that the state effect is included in the final effects E. On the other hand, a handler for H from the effect will eliminate H itself in the effect list in this monad. And there are also a few other variants of handlers that we will explain as we use them. Now, let's see some examples. The first example is about exception. Here, I declare an exception effect with a single operation throw, which takes a unit and returns an integer, so it is specialized for this particular example. We can use the effect to define a safe division function that first tests whether n is 0. And if it is, it will throw an exception, or otherwise it will return m divided by n. Note that this function does not say what would happen when an exception is thrown. The handler hdefault handles this exception by declaring a handler clause using this operation function, which is just one way to define handlers using our framework. And the handler resumes the original computation by calling k with a default value 0. So under this handler hdefault, div42.0 will return 0, while div42.2 will return 21. And because the definition of div does not specify the semantics of throw, we can easily use a different handler to handle the same operation. For example, hmaybe changes the return type of the program to a maybe type. It uses the handler return function, which takes an extra function that is applied when the computation returns a result. If the computation returns a result, the handler will wrap the computation result inside a just. And if an exception is thrown, the whole computation will return nothing. This is an example where we do not call k at all at the definition of the handler. So under hmaybe, div42.0 will return nothing, and div42.2 will return just 21. We can also call k multiple times in a handler. On this slide, we define an effect ndet, which has a single operation flip that takes a unit and returns a Boolean. And the handler hndet resumes the computation multiple times by calling k with true and false respectively, and then concatenates the results. And if a computation returns normally, the return clause of the handler will wrap the computation result inside a singleton list. So if we call flip twice as a program at the bottom of the slide with the result bind to x and y, and then we return x and y, we will get 4 Booleans corresponding to when x is true, y is true, x is true, y is false, x is false, y is true, and x is false, and y is false. We also remark that effects and handlers are composable. For example, the program toEffects on this slide uses both flip and throw. And by composing the two handlers differently, we can get the result either as a maybe of a list, in which case this is just nothing, or a list of maybes. And that's all about the background of effect handlers. Now we go back to choice-based learning. Recall that what we want is to implement the training program using effect operations and the optimization techniques as effect handlers. We start first with the training program. The program on the right of the slides corresponds to the training algorithm on the left. We define the effect choose with a single operation called choose. The program on the left is a loop, but on the right, we focus on one iteration, which takes one training example, x and y, and the current parameters, w and b. Then the program corresponds roughly line by line to the pseudocode on the left, where we first choose the new parameters by passing the current parameters as arguments, and then we compute y prime and compare y prime to y to calculate the loss. Since this is a single iteration, we return the new parameters to be used for the next iteration. Here, loss is a built-in operation for a writer, which we will explain later. At the second half of the example, we want to define the optimization technique, in this case, gradient descent. The program on the left of the slides shows an incomplete definition of gradient descent as a handler. The handler takes the current parameters as arguments and suppose that we have a way to differentiate the loss with respect to the current parameters. Then we can update the parameters as the original parameters minus the gradients and resume the original computation with the updated parameters. By implementing the training program this way, we can get the advantages of programming with effect handlers. For example, we can implement different optimization techniques as different instances of the handlers, and we can easily have multiple choices and as well as other effects for the program, all inside a single unified framework for effect handlers. The only problem left for now is what to put in this question mark box. That is, what is the function we should differentiate with? Ideally, we want it to be the loss function of the training model. But the handler is defined separately from the training program, so it has no idea what the loss function of the training program would be. And this is how the selection monad comes into play. Specifically, the selection monad has the form given on the top of this slide. And the people who are familiar with the continuation monad may have noticed the similarity and the differences between the selection monad and the continuation monad, where for the continuation monad, it goes from X to R, but for the selection monad, it goes from X to R to X. An interpretation of the selection monad is that, viewing R as a set of losses, a computation of this type is a selection function which takes another function, which we call the loss continuation, in X and R, and then picks an element in X. An example function of this type is argmax, which takes the function f and then returns the set of elements at which f is maximized. Our work is also inspired by the work by Abadi and Plotkin, which connected the selection monad with choice-based optimization. And they show that the selection monad semantics with the optimal selection functions corresponds to the operational semantics that always choose the optimal execution strategies. But here, instead of focusing on the optimal semantics, the selection function in our framework is written using effect handlers with user-provided semantics. We can encode the selection monad in Haskell like this. I'm not going to go through the definitions in detail, but people who are interested can verify by themselves that the definition satisfies the monadic law. We can also combine the selection monad with an auxiliary monad to account for additional effects. And the resulting STX is also a monad, given that some conditions are satisfied. For example, we can combine the selection monad with the writer monad, and we get SWX, which is also a monad that takes a function in X to R and returns a tuple of an R and an X. Having introduced the selection monad, now we want to connect the selection monad with effect handlers. Specifically, we are going to interpret the effect handlers in the selection monad extended with the writer monad. Here, I simplified this interpretation because in practice, we also needed to extend the writer monad with a multi-set of uninterpreted effects to account for algebraic effects. So through this interpretation, we get two key features of the system. First, the loss operation we have seen before is a built-in effect for writer that writes the loss. And since it's a writer effect, we can naturally have multiple losses in a program which will be combined together. Second, now the handler will receive an extra parameter, which we call the choice loss continuation here in LK, that takes the operation result and returns the loss associated with the operation result. And notably, the loss will depend on the operation result, or it may depend on the operation result in a very complicated way. To demonstrate how this all works, we will go back to our running example with gradient descent. But before that, let's first look at the current selection monad-based effect handler programming interface. The interface is very similar as before, except that we use the selection data type, which takes a loss type A, a loss type R, an effect E, and a type A. And the losses must form a monoid since it's part of the writer effect. You cannot really see it here, but here's operation data type op also takes an extra up parameter. But just like before, we will always omit those polymorphic type parameters in the rest of the talk. With that, we can go back to our definition of gradient descent. Previously, we did not know what to put here as a loss function that we should differentiate. Now the answer is easy. As the handler gets an extra choice loss continuation LK, we simply put LK here, which represents the loss function with respect to the choice of parameters. Putting all pieces together, this slide summarizes the example for gradient descent. We can also write down the definition of K and LK in the definition of handlers explicitly for this particular example. Here, LK will return the loss associated with the choice for W prime and B prime, so that you can see the differentiation will go correctly and we have successfully implemented one step of training. Here, the K will return a tuple with the first element being the loss and the second being the original computation result. More generally, the definition of LK will be derived from the definition of K, so there will be no code duplication, and LK is not necessarily equivalent to the first element returned by K. These slides summarize the definition of the selection data type, and I will also talk at a high level how the selection monad is implemented. The definition of the selection monad in our case builds on top of the F monad we have seen before. The loss continuation in the selection monad has type A to FER, and the result of a program is a tuple of the loss value and the computation result. Intuitively, we can consider the source program is implemented via a transformation, where the source program is written in the selection monad, which takes a loss continuation and goes to a program in the target monad. As an example, a handler definition in the source program, which takes this additional choice loss continuation LK, is translated to a normal handler definition in the target program. And this translation allows our implementation to easily target other effect handler languages. A brief summary of what we have talked about so far. We proposed to implement choice-based learning using effect handlers interpreted in the selection monad, where programmers can naturally define their own choice mechanism as operations with associated losses and optimization strategies as handlers. And due to the nature of effect handlers, multiple choices and different optimization strategies can be easily combined. In the rest of the time, we will see some more learning examples using the interface we developed. We will talk about 3 examples: hyperparameter optimization, generative adversary networks, and reinforcement learning. In machine learning, hyperparameters are the kind of variables that are not directly related to the training data, but governs the training process itself. And we have already seen one example of hyperparameter, which is the learning rate we used for gradient descent. And we must be careful when choose a good learning rate, as demonstrated by the figure on the right. Training with a very small learning rate can take longer to converge, while training with a high learning rate may be less stable or even diverge. And the process of searching for best configurations of hyperparameters is called hyperparameter optimization. Take the learning rate as an example. We can define effect for choosing a good learning rate. The definition of the handler shows one example handler definition that simply chooses between 2 learning rates, A1 and A2. The handler simply compares the 2 losses associated with the 2 learning rates and returns the one with smaller loss. And we can also combine the handler for learning rate with the handler for gradient descent. First, we can make the original handler take an extra argument which represents the learning rate as an argument. And we can then combine the handler for the learning rate, as shown at the bottom of the slide, and choose a learning rate A and pass A to the handler for gradient descent. This example shows that for multiple choice decisions we need to make, we can implement them using nested effects and handlers. Our second example is generative adversary networks, or GANs for short. GANs are a framework for generative AI. The key idea is to simultaneously train two models that contest with each other, a generator that learns to generate samples, and a discriminator that evaluates samples and estimates the probability that a sample comes from the real data distribution rather than a generator. And gradually, the generator will become better at generating samples that can deceive the discriminator. In essence, GAN is a min-max two-player game with the same loss. With that in mind, we can implement GANs as two effects and two handlers for the same loss function. But one tries to minimize the loss and the other tries to maximize the loss. The GAN program on these slides takes one real data point and one noisy data point and the current parameters for the generator and the discriminator respectively. And then each model makes its own choices, but then they share the same loss value that actually refers to both parameters. And the last example we are going to show is reinforcement learning. Perhaps one of the most well-known examples for reinforcement learning is AlphaGo, which defeated a Go world champion in 2016. Generally speaking, reinforcement learning is where an agent takes actions in an environment in order to maximize cumulative rewards, as shown on this diagram, by this diagram on the slide. At each time step t, the agent receives the environment state st, and based on that, it selects an action AT. At the next time step, t plus 1, the agent receives a reward rt plus 1 and finds itself in a new state, st plus 1. The output of reinforcement learning task is a policy that defines the agent's the way of behaving. For example, as a mapping from the current state to an action to be taken so that the agent can achieve its goal by following the policy. Recently, Lago and others also proposed the use of effect handlers for reinforcement learning. But they did not support the loss continuation, and as I will explain later, it seems unclear how to modularly combine reinforcement learning and gradient descent-based approaches using their frameworks. The agent environment interface turns out to fit extremely well into an effect handler framework. In particular, we can implement the environment and the learner as two effects, where an environment has one operation observe that takes an action and returns a reward and a new state, and the learner has two operations, predict takes the current state and returns an action to be taken, and the feedback operation provides the observed transition to the learner in the hope that the learner can learn from this transition to make better predictions in the future. We can then implement the agent as the program on the slide. The agent takes in the current state and performs three operations. A step of predict that gets an action based on the current state using the learner, and a step of observe that takes the action and gets a new state and a reward from the environment, and a step of feedback that provides the observed transition to the learner. And suppose we have a function isGo that checks whether the agent has reached its goal. And if not, we will recurse using the new state. As a concrete example, we consider a standard task of cliff walking in reinforcement learning. In this case, the agent has a start state S and a goal state G. And each state is a tuple of coordinates of a position. The action is to move the agent up, down, left, or right. And the agent receives a reward of -1 on all transitions, except those into the region marked cliff, in which case the agent receives a reward of -100 and gets sent immediately back to their start. The output of learning is a mapping queue that maps a state and an action to a reward. When we have the output queue available, the agent can behave following queue using, for example, a greedy policy that always chooses the action with the maximal rewards. In this case, our goal is to find a path from the start position to the target position while avoiding the cliff. Using the effect handler interface, we can implement different learning algorithms as a handler for the learner effect. I'm not going to give you the complete definition, but we can easily implement standard reinforcement learning algorithms, such as Q-learning. Because both operations need to access or update the Q mapping, we use parameterized handlers that keeps track of Q as the handler parameter. And this path in blue in this figure shows the policy learned by Q-learning, which travels right along the edge of the cliff, thus getting to the goal with a maximal cumulative reward. Again, we can easily, with effect handlers, we can easily implement other reinforcement learning algorithms as different handler instances. For example, implementation of another standard reinforcement learning algorithm, SASA, will output a different path. A detailed comparison between reinforcement learning algorithms is out of the scope of this talk, but I will remark that this path through the upper part of the grid is longer but safer. Namely, it has a lower possibility to fall off the cliff. And a final remark I want to make is that for this particular reinforcement learning example, the role of the loss continuation is not obvious, as we may implement the example using just effect handlers, but not effect handlers with the selection monad. But even in such case, the implementation has already made it clear that effect handlers can provide a modular interface for writing reinforcement learning algorithms. In practice, the state space can be arbitrarily large, and we cannot expect to have a complete Q mapping. So one often wants to combine the reinforcement learning algorithm with, for example, the gradient descent approach we have seen before to learn the mapping queue. And for example, we can have the loss expression inside handler definitions, and then have an upper handler that learns the Q mapping using the loss operation. And our framework makes such combination very easy. To summarize the talk, our motivation is a study of a general language design for machine learning programming. We proposed that a specific kind of learning, which we call choice-based learning, can be implemented by combining algebraic effects and handlers with the selection monad. And we have seen examples with gradient descent, hyperparameter optimization, generative adversarial networks, and reinforcement learning. There is more to this talk that is not there is more to this work that is not included in this talk, including an algebraic effect calculus and its type systems, and a formal transformation from effect handlers with choice loss continuations to normal effect handlers, which allows us to target other effect handler languages, as well as the denotational semantics of the effect handlers based on the selection monad, along with the proofs that the translation preserves the denotational semantics. And you should really ask Gordon for this. With that, thank you for your attention, and I'm happy to take questions.
We have a bit of time for questions. Whoever wants can step up to the mic. Until then, let me ask one. So thanks for the talk. This was a really cute way of writing down all these machine learning algorithms. There were a couple of details that were hidden from the implementation, like the autodiff or something, or how you implement the neural networks in the back. So last time I checked this out, which admittedly was 7 or 8 years ago, there were 5 different libraries for encoding neural networks and 4 different libraries for doing auto differentiation. is like a newcomer for this? Is it any better now in the Haskell world, or what would you use? What do you propose a newcomer look at in terms of implementing the underlying details of this?
Right, that's a great question. So just to expand the relation between our work and like other like programming paradigms, our work is sort of orthogonal to like differentiable programming in the sense we don't really like deal with automatic differentiation, but we would benefit from having an automatic differentiation function because as you have seen in the definition of the handler, we actually use autodiff to try to differentiate the loss function. And we implemented our design as like a Haskell library, sort of like to demonstrate that our design like works, like as a proof of concept. But our ultimate goal is not to do machine learning using Haskell. So in the end, I think we want to implement our design to like more realistic machine learning frameworks, like for example, JAX. So yeah, so this is like a proof of concept, but we have this we have this library available, and we will release it later so like people can actually use it to try do machine learning programming.
Awesome, thank you.
Hi, I'm Shuhao from Bloomberg. Very, very exciting talk, and I find it amazing when you show the slides where you combine the hyperparameter learning and the gradient descent algorithm using a nasty effect. Just one question regarding portability of the work to other effectful language. For example, in one of your slides, you mentioned OCaml has an effect handler. So I'm just wondering, for example, but the effect handler in OCaml does not support, at least from the standard, does not support multi-short continuation. It's kind of linear continuation. So do you think this limitation will create a burden in terms of, for example, really implement your work in OCaml, or it's not crucial?
Right, that's a great question. In some sense, I think like having multi-shot resumptions would be good for writing just machine learning programming in general. But also, I want to go back to the slides where I show the automatic differentiation. Here, okay, not this one, the next one. Okay. So in some sense, like the loss continuation LK is sort of like derived from the definition of K. So like calling both LK and K is like a multi-shot resumption. So I'm not sure like this is doable like in languages like OCaml, but I also want to remark that here we're actually not calling K in this case. We are like differentiating this LK. So it's like somewhere between like a single shot resumption and a multi-shot resumption, and I don't exactly know what that is. But if we only care about differentiation but not like actual resumption, it might be doable, but I'm not sure.
Thank you.
Ron Minsky, James Street. I'm curious if you could say a little bit more about what your plans are for embedding these kind of ideas in a system like JAX, where Python does not, last time I checked, have an effect system or any of the kind of type level structure that you have in Haskell. So what's the idea for how this kind of idea might translate to that kind of environment?
Right, that's a great question. So actually, like one plan for this work is we want to implement it in JAX. So that means we want to implement effect handlers for JAX and as well as effect handlers interpreted in the selection monad. But that's not easy because JAX lowers to XLA, and then we have very few control over like how the continuation is going to be captured at runtime. So there's like some challenges there, but we definitely want to do it in a realistic machine learning framework. And we are especially interested in implementing it in JAX.
Any more questions? If not, let's thank our speaker again.
2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4.
stand so we don't like get terrible feedback. Hello, hello. I am speaking. I'm speaking to you. I'm speaking to you with my voice. Testing 1, 2, 3. Great. I can keep talking. Still talking. Saying. Oh, there we go.
Yeah, people can
Great.
hear me.
People can hear me. That's good. That's what I like to hear. All right. Thanks, everyone, for coming to the random testing session at the Haskell Symposium. Our first speaker today is going to be Ed Vries, talking to us about shrinking.
Thank you very much. 11 years ago at the Haskell Symposium in Denmark, Copenhagen, Denmark, Koen Klaassen presented a brilliant paper, a functional Perl. At the time, QuickCheck was able to generate functions, but not show them, never mind shrink them. And Koen Klaassen showed how to do this. It's a great paper. It's mind-blowing. I recommend reading it. But what Koen did in his presentation, he started with a demo of a simple property that uses a function that's being generated and shrunk. And since science is all about repeating things, I want to show you a similar demo before I move on to anything else. So here is a simple property written in the language in the library called falsify. So in this property, what we're doing is we're generating a random function from a list of word 8 to a Boolean by calling a function from the library called fun, which takes as argument a generator for the results of the function. In this case, we're generating random Booleans. The false argument there, by the way, is saying we're going to shrink towards false. And now we're going to assert about this function that if we apply this function to the list 3, 1, 4, 2, we should get the same answer as when we apply it to the list 1, 6, 1, 8. Right, so this property is saying that for any function from a list of word 8 to bool, that function should give you the same answer for these two lists, which of course is clearly nonsense. Right, so we should have a counterexample to this. So when we run this in falsify, then we're going to get a counterexample. And in this particular case, the counterexample that we got was a function at the bottom here, this generated line here. And this function says we're going to return true for the list 1, 6, 1, 8, and false everywhere else. Right? So this is an obvious counterexample to the problem. And it's a nice, beautifully minimal counterexample. And if we run this again, we might get the same answer, or we might get one different. In this case, we happen to get a different one, which is a function that returns true for the list 3, 1, 4, 2, and false everywhere else. Right? So these are the only two counterexamples you're going to get. Right? These are the only minimal counterexamples to this property.
Is this what QuickCheck does today?
This is similar to what QuickCheck will do today, yes. Except this is a falsify what you're looking at. But yes, QuickCheck will do this too. And Koen showed how to do this in QuickCheck. But I did not write a shrinker. Right? That's the point. So Koen showed how to write a shrinker for this. The point of falsify is that you're not going to write shrinkers. You get shrinking sort of implied in your definition of a generator.
Failed after 59 shrinks.
Yes. Yes, indeed. So this is how it works in general, right? When you do property-based testing, you generate some large counterexample. You're going to get lots of unnecessary detail. Then you throw out the unnecessary detail, and then you end up with the counterexample that you're actually interested in. And in this particular case, the function that we're generating is infinite. And so it's very important that we shrink it, because we don't want to show you an infinite function. It's infinite because it has a value for every potential input, right? OK. So I want to talk about falsify, and I'm going to do this by placing it in context of the existing libraries for Haskell, in particular, of course, the granddaddy of them all, QuickCheck. And so in QuickCheck, how do we do property-based testing? Well, a generator in QuickCheck is a pair of two functions. Right? We have a function that produces a value from a random number generator. And then, like we just said, that probably, if we find a counterexample, that counterexample probably has lots of unnecessary detail. And so we need to shrink it. Right? We need to come up with smaller counterexamples. Now, this works quite well, but the problem with this definition is that it has very limited composability. So in particular, for example, we cannot give a functor instance. Right? For a functor instance, we have a function from A to B and a generator for an A, and we need to give you a generator for a B. Now, the generation part is easy. We just call the generator for an A, and we call our function to get a B out of it. Easy enough. But the shrinking is impossible. Right? We have a shrinker, a function from A to list of A, and we need to produce a function from B to list of B. So we have a B, but we can't apply the function. We would need a function from B to A before we can call the underlying shrinker. Right? So this is not definable. Now, this is a well-known problem, and in Cubic QuickCheck, introduced a long time ago, they solved this problem by using integrated shrinking. And in the Haskell world, this is most well known from the library called Hedgehog. And in this case, a generator is a function from a pseudo-random number generator, as before, but now to a tree of values. Now, the root of this tree is going to be the original value, right? The original produced value. And then values further down the tree are shrunk values. So this has an obvious functor instance, right? We just map the function over the tree, very easy. And it also has a very good applicative instance. So for example, if the tree on the left here, this 2, 0, 1, 0 tree, that might be a generator that produces a 2, which can shrink to a 0 or to a 1, and that 1 can shrink to a 0 again. Right? And then maybe you have another tree, we produce a B, which can shrink to an A. And then we can pair this up very easily. Right? How do we pair them up? We just take the roots, and then we either shrink the value on the left or shrink the value on the right. Very simple. So applicative instance works very well. Where this falls down is in a monad instance. And the monad instance is important, right? Because when we're generating arbitrary values, we very often need monadic bind. For example, when we're generating a random list of values, we need to pick a length, and then depending on the length that we choose, we need to produce that many elements. Right? So the effects that we need clearly depend on values that we generate earlier, which is clearly a monadic bind. And so in the Hedgehog world, what does this look like? Well, we might have this tree, right, the 2, 0, 1, 0 tree that we had before. That might be our length. And then you can imagine that for every length that we pick, we have a tree of potential trees, a tree of potential lists of that length. Right? So we have a tree of trees, which is the picture on the left here. Now the problem is, how do we flatten this tree? And the answer is, we basically cannot. There is no good way to do it. And picture B here is the normal way that people do it. What you should note about this picture is that when we go, for example, from BB to AB, right, so we shrink one of the characters, we never go back anymore and shrink the length of the list. And this is a general property of integrated shrinking. Like every monadic bind introduces a cut point. Right? We shrink on the left, we make a decision. Once we start shrinking on the right, we never go back anymore and shrink on the left. And if you think about it, this actually makes sense because monadic bind, we have a function on the right-hand side. Right? So we have a generator, produces a value, which we can shrink. After we apply our function to a shrunken value, well, then we can start shrinking on the right. But if we now go back and shrink on the left again, the only thing we can possibly do is reapply our function and start all over again. Right? So this is inherent to this approach. Now, the Python library called Hypothesis showed us how to do this in a different way. And in the paper, there's a detailed comparison to the Python library. I'm just going to focus on what Falsify does here. Now, the key idea from Hypothesis is that we're not going to interpret a pseudonumber as a function, a generator, as a function from a pseudo-random number generator. Instead, we're going to unfold the generator of pseudo-random numbers, get samples from this generator, and then we're going to parse these samples to produce values. Right? And we saw this earlier in the talk about internal shrinking with bidirectional parsers yesterday, I think. So this is the same idea here. Now when I first heard this at Haskell X last year, I thought it was completely bonkers, but actually it works surprisingly well. And so what we do in Falsify is we don't unroll this as a stream of values. Instead, we unroll it as a tree, an infinite tree of values. Right? So if you have a pseudo-random number generator, you can split it right, into two independent generators. Those are your two subtrees. Or you can draw one value from the generator. That's the value that's there. Right? So the idea is that you're either going to use the sample or the two subtrees, never both. Now this tree is always infinite, conceptually at least, but we have a finite representation of the minimal tree that is 0 everywhere. It's an important optimization, but I'm not going to focus too much on it. But you can think of this as an infinite tree, and so we can have a view pattern on this that says, well, any tree you can think of as an infinite tree. We can always pattern match on it. If it happens to be the minimal one, then the sample you get out of it is 0, and the two subtrees are also 0. And I'm going to use it.
Should I think of it as just a random number generator, but splittable?
Yes, yes, yes. A splittable random number generator. Yes, absolutely, yes. Okay. So then as a first approximation, a generator is simply a function from one of these trees to a value, right? A parser of this tree to a value. Now that doesn't quite work, because these trees are infinite. Right? So if you think about it, when I'm shrinking, what I'm going to do is I'm not going to shrink the resulting values anymore. I'm going to shrink the input to this function. Right? I'm going to shrink the samples that we get from the random number generator. That's the whole point. So you're not going to write a shrinker. You're just going to reapply your function after shrinking values in this tree. But this tree is infinite. Right? So if I'm shrinking by shrinking this tree, I can always find a value somewhere to shrink, which is irrelevant to the function that I'm using because it might not even look at it, and so shrinking would not terminate. Right? And so we need to know where in the tree that we're shrinking. And so we're actually not going to use we're going to use this definition instead. A generator is a function that takes a sample tree as input and gives you a value along with the possible ways to shrink this sample tree. And the main idea here is that this is primarily so that we can sort of know where in the tree is useful to shrink. And so, for example, here's the most primitive generator of them all. It just draws one value from this tree. Right, so what do? We pattern match on this tree. We use this inf thing to always pretend that this tree is always infinite. The value that we return is just the value at the top of the tree. And the only thing that we can shrink, we just replace the value at the root of the tree by smaller values. Right, so this is like binary search or something like this, like the normal way that you might shrink samples in quick check or something like this. Okay.
So the subtrees are just completely ignored here?
The search tree is completely... The subtrees, yes. The subtrees are completely ignored. Yes, the only value that is relevant to the primitive generator here is the value at the root of the tree, and so the subtrees we just leave alone. Yes, correct. Okay.
So I'm still not getting it. So the subtrees returned, the S trees returned.
Yes.
You could give to run again to generate a fresh value. Is that the idea? What are you going to do with the S trees that are returned?
Oh, I see. What are you going to do with the S trees that are returned? So the idea is that you shrink it.
Yeah.
You then test if the shrunken value is still a counterexample. And if it is, you might repeat the shrinking step again. Right? So you shrink one step, maybe somewhere down, maybe this is compositional, right? So maybe I shrink something over here. I check, is this still a counterexample? If so, great. I will try to shrink again, and now maybe I find something somewhere else. Right? So that's why
So you apply run to the shrunken tree to get the shrunken value.
Yes, we get the shrunken tree, we reapply our parser, we get a value out of it.
Okay.
Yes, correct. Yes. Yes. Now, please, yeah, questions are very welcome, for sure. Okay, so now let's go back to the example that we had before with the list, right? So we pick a length, and then we just generate a bunch of values. So with Hedgehog, we said we had nothing to shrink, right, on the right-hand side of monetic bind, because we didn't have a value. But that's not what's happening here. We're not shrinking values, we're shrinking the input to these values. Right? So we have this infinite tree. For monetic bind, what we're going to do is we're going to take the left subtree and use it for the left generator, and then we're going to take the right subtree and use it for the right-hand side of the monetic bind. And now we can shrink these trees independently from each other. So in this particular example, we might have a sample tree that has at the top, this 3 is going to be the length of the list that we choose, and then the values further down are the values from the list that we're generating. And so now we can go back and forth very easily. Right? We can go from this list 1, 1, 0, we might shrink one of the elements in the list to get 0, 1, 0. Now we might go back, maybe shrink the length of the list, get something else again, right? And we can go back and forth between left and right very easily. So this is much better, much more composable, even across monetic bind. So I want to give you some intuition on how you write generators in this way. So prim is going to be our building block. And every time that you write a generator, the thing you have to ask yourself is, how does my generator shrink if the generators that I depend on shrink? Right? So prim is going to take a random number and is going to shrink towards 0. Right? So how do we, for example, make a generator that produces a bool? Well, we just draw a random value in the full range of word 64, and then we just check, is this value more than the halfway point? Right? So that will give us a value either 0 or false, false or true, with equal probability. Right? And now as this value that's produced by prim shrinks towards 0, our generator will shrink towards false. And again, this looks similar to how you might write a generator in other paradigms, right? But we're not writing a shrinker, right? The shrinker is implied. Now, you can get this wrong. For example, suppose that we want to write a generator that produces a value up to a certain maximum. And we might do this simply by taking mod, our maximum, right? Now, if you think about it, if the value that we get from prim maybe shrinks from, say, 101 to 99, and we take mod 10, right? Then our value that we're generating is going to shrink from 1 to 9. It's going to go up instead, right? So that's not a good shrinker. So what you could do instead is, for example, you can write a generator for a fraction, right? So we just call prim, we divide it by the maximum value that prim could ever return. Now you get a fraction between 0 and 1, shrinking towards 0. And then our below, well, we just produce a random fraction, and then we just multiply by our maximum. Right? So as prim shrinks towards 0, the fraction will shrink towards 0, and therefore this value produced by below will shrink towards 0. Yes, question?
Is there a way to write the Boolean generator so that it knows that it only ever has to shrink once?
The question is there a way to write the Boolean generator so that it knows it can only shrink once? Yes, there is. But ask me again if we have time at the end. But yes, we can. Okay, as another example, suppose that we want to write a signed fraction, right? Using the generator that we had before. One intuitive way that you might do it is you just draw a random Boolean and a random fraction, and then if the Boolean is false, it's positive, otherwise it's negative, or the other way around. I forget what I did. This doesn't work very well because as that Boolean shrinks towards false, we're now going to always produce negative fractions, right? That's not a very good shrinking behavior. Probably we want a generator that shrinks towards 0, no matter where we are coming from. Right, so what we could do instead is we generate 2 fractions and just pick the minimum one. Right? This will give you better shrinking behavior. So people like to say shrinking comes for free in integrated or internal shrinking. Shrinking never is free. Right? You always have to think about shrinking.
Tell me about the 2 fractions again.
So in the 2 fractions case, we generate 2 independent fractions that can both shrink independently. And then we just pick the one that is closest to 0. Yes, question?
I guess you haven't shown us the shrinking of the bind, but I would expect that it tries left and right, and therefore we also get the case where it shrinks the fraction call, even keeping the Boolean true. So wouldn't you also shrink from the negative here?
Yeah, that's true. So monetic bind shrinks on the left or on the right. So you could shrink on the other side, but the moment that Boolean becomes false, there's a very strong bias towards the negative ones. Yeah. Okay. This is a very important example. Suppose that we want to choose between 2 generators. Then what we could do is we just pick a Boolean, and then if the Boolean is true, we pick L, otherwise pick R, right? Now, the problem with this definition is that what we're going to do in this case is we're going to suppose that this Boolean is currently true, right? So we're picking L. Now we're shrinking the sample tree with respect to L. Now if this Boolean then shrinks towards false, we switch to using R, but what we're going to do is we're going to pass that very same sample tree that we were using for L before now to R. And any of the shrinking that we did with respect to L might be completely irrelevant for R. Right? So this is not a very good definition. Now, in a way that is fundamental to this approach, right? There's always going to be cases where we use a sample tree in one context and then suddenly reinterpret it in a different context. That's unavoidable in the general case. But falsify gives you some tools to avoid it in some cases. So this is suboptimal. I want to show you a version that is completely wrong before I show you the proper version.
Is the second problem here that you shrink the Boolean to false and then you stay?
Yes, there's a second problem there too. Yes, yes. So we might be tempted to do something similar that we did before, right? So we just generate both sides and then pick one. The problem here is that suppose that this Boolean is currently true, and so we're using one of the two generators. Then falsify starts shrinking, and it notices that the sample tree that we're using for R is completely unused, right? Because nobody's looking at it at the moment. Therefore, we can shrink it to the minimal sample tree. Right? Therefore, if we then try to switch, the only sample tree that we can run this with is the sample tree that is 0 everywhere. Right? If that happens to work, fantastic, but in most cases that's not going to work. Right? So what we want to do, the problem here is that it's not visible to the driver, right, the falsify driver, that we're making a choice. Right? This choice is embedded in this pure function here, but it's not visible to the interpretation of the gen monad, right? What we want to do is we want to prevent an effect from happening, in this case shrinking, when we're not using something. Put another way, we want to selectively shrink, right? We know how to do that. That's a selective functor, right? Which does precisely this, right? Selective functors make that vec that we're making a choice explicit, right? So in selective functors, we have an f of a bool that says which one do we want, and then two generators, well, in this case, two generators, right? And we just pick between them, right? And now we can do what, and now choose is just if s, right? It has a selective instance, therefore it knows what we're choosing, and it doesn't try to shrink the other part of the tree. So this is a very useful tool that in lots of building blocks.
But we don't want to shrink the bool either, do we? Because then you fix on one tree. You've still got a Boolean generator that will get shrunk to false all the time.
And that depends on your, well, if you have a generator for the bool that shrinks towards false, then your choice is going to do that too, right? But in this particular, I mean, you could have any generator for bool that might toggle, that might, this bool might be generated in lots of different ways, right? It might not have that strong bias. Yes. Okay. There's a very useful generalization that we can make, where we add one little bit of state, and I literally mean one bit of state. What we're going to do is we're going to add to sample whether the sample has been shrunk, yes or no. So the initial sample tree says not shrunk everywhere, and then the moment that we start shrinking, we record that we started shrinking. This gives us just enough information that we can write functions like this, where we have very explicit control over how we're going to shrink. Right? The definition in the paper, but you can imagine that we can just look at the tree. If it's not shrunk, then we're going to give you the x that you want, right, the original value, and if it is already shrunk, we just add enough state into the tree that we can produce the other values here. That's a very useful combinator. For example, we can taking a gen A to a gen of maybe A in this manner. And what we can do now is an answer actually on the question from Simon PJ last year at HaskellX when somebody was talking about this hypothesis. And Simon asked, can we use manual shrinking in the context of internal shrinking? And the answer is, yes, we can, with this additional bit of state. So what we're going to do is we have this initial thing that's going to throw away all the sample trees that we have. Like, we just keep the original one. This cannot shrink, right? This is just a generator that can't shrink at all. Then, if we have a tree of values, like hedgehog style, right, we can produce a generator for it simply by using the shrink to, right? We start at the root, and we shrink towards the trees recursively, the subtrees. And now we can provide a combinator that, given a manual shrinker from A to list of A, we can produce a generator by throwing away all the original ways that this was shrinking, reconstructing the tree of values, and then using that. So this gives us a way to embed, if you need to, a manual shrinker. Okay. So I'm not going to talk about in detail how we generate functions. Actually, it's very similar to what Koen does in his paper. You have some definition of concrete functions. Nil is the function that uses the default everywhere. We have the way to tabulate functions, which we only do for small functions. And then there's sums, products, things like this, right? And then just like in QuickCheck, we have a class that produces these things. Actually, in QuickCheck, there's two classes. There's co-arbitrary, which a lot of people find quite confusing, and there's function. Here is only one class, and I think it's a more intuitive thing. It just says that given a generator for the codomain of the function, produce a concrete representation of the function for the domain. And Falsify is very carefully designed so that this works, right? That we can generate these infinite structures. These functions are infinite, right? It gives you a value for every possible input because we don't know ahead of time which input you're going to need, right? Only once you apply it to a property, only then do we know, right? And then we can start shrinking, throwing away parts of this thing, and then ending up with a finite description of this function, which is a counterexample. Okay. Should you use this? And this is the point where I should tell you, yes, you should all use it. I'm not going to do that. I had the privilege of working with John Hughes a couple of years ago. We were teaching courses on testing before, and I learned so much from John that completely changed how I think about shrinking. Right? I am obsessed with shrinking. So I think very carefully about my shrinkers. And if you want to think very carefully about your shrinkers, then possibly QuickCheck might be the best choice, right? Because you're very explicit about your shrinkers. But many people are much less obsessed than I am about shrinking for some strange reason. And so they don't want to think about shrinking. And in that case, I think Falsify might work quite well for you because you get an implied shrinker that is probably not as good as a carefully handcrafted shrinker, but it's probably a lot better than no shrinking at all, right? Now, that is the same claim that people make about Hedgehog or integrated shrinking, but then magnetic bind has all these cut points, right? So you get a very poor shrinker in many cases. I have no big case studies in Falsify, right? So I have no evidence to say that this actually works, except that in Python it's very popular, right? People in Python really say that this works very well for them. And I would say this is like Python, but better. So I don't know. Yeah, so that's all I have for you. We already have a bunch of questions, but if there's any others, then I'd be more than happy to take them. Thank you.
This is super cool. Thank you. I wonder if, you know, it seems like there's some ways that you can write this where you don't get the shrinker you want, or at least you get a worse shrinker than you want. Have you thought about ways to either statically or dynamically get some information about that?
Yes. Not statically, but I talk about this in the paper and also in the library. There's quite a few combinators in the library that help you precisely to test your shrinking. When people say shrinking is free, no, shrinking is not free. You need to think about this, and you can get it wrong. So the library gives you tools to test your shrinker, and then shrink the counterexamples to your shrinker too. So yeah, I didn't have time to talk about that, but yes, it's in the library, and in the paper. Yes.
Very cool, thanks.
So this seems like this is obviously oriented towards shrinking, but it seems like kind of a really nice way to do like composable generation in general. So do you think there's any potential to like use the same underlying data structure, but not just shrink, but maybe do something for like like composable procedural generation or anything like that?
I mean, maybe.
Like
I don't know whether it
like
really changes anything fundamentally about the generation part.
What's it about like making it composable and being able to like get the determinism out of it? I don't know.
Yeah, but even QuickCheck is composable just for the generator, right? It's the shrinker that's the problem. So I'm not sure if this
Maybe I got to think about it more.
Yeah, thank you, though. Yes.
I'm surprised I didn't hear the word monotonic. It seems like there's
Oh.
very sort of order theory, latticey things going on with this and shrinking, especially the shrinking the both sides and the Boolean example, where
Yeah.
you essentially want to you want like an unbiased product there and not the total order on Booleans. Has this come up at all in your work or?
Yeah, so it's a good question, and I talk more about it in the paper too, but the monotonicity comes from two things. First, the library guarantees that all it ever does, the only way that the library shrinks, is samples going towards 0. Right? And this is one big difference with hypothesis. In hypothesis, you have this, I don't know, there's 14 or 15 different ways that this tree is shrunk and growing, right? And they're proud of it too. Here you have one, right? So it's much more principled in that way. Now, of course, you might still write a generator that is not monotonic, right? Not monotone. For example, the wrong below that I showed you, right? Even if the samples are shrinking towards 0, that was cycling through something, right? It was not monotone. So that's one of the proof applications that you have as an author of a generator to get that right. And the library gives you tools for testing it. But yes, it's something that you need to think about.
Great, thanks.
All right. If you would have one more quick question.
Quick. So, in the talk that we had yesterday or the day before,
Yes.
the bit that went from the S tree to the value
Yes.
turned into this bidirectional lensy thing.
Yes.
Do you think, I mean, this is speculating a bit, is that approach compatible? Could you combine that bidirectionality with the stuff that you're doing?
Yes, we talked about this yesterday. It's an interesting question.
Or is it, the selective functors and the monadic binds? That doesn't sound so bidirectional to me.
It doesn't to me either. I am not sure. I think the devil will be in the details there. Also, the fact that this thing is completely, like the emphasis on infinite data structures here too, right? The on precise treatment of laziness might also get in the way of the bidirectionality. So I think that's an interesting question, but maybe these guys can do another PhD on this or something.
Fortunately, PhD student.
Oh, yeah.
All right, let's thank our speaker
Thanks,
again. Just make sure this gets set up. Please hold. And very pretty, but it's not slides yet. Still is. Okay, good.
I am plugged in. It just takes.
How many computer scientists does it take?
It just takes its time.
Hey, there we go. All right. So. All right. So our next speaker is Segev Elazar-Middleman, who is going to be speaking to us about enumeration and property-based testing.
Thank you. Hi, everyone. I'm Segev Elazar-Middleman. I'm here to tell you about our paper, Don't Go Down the Rabbit Hole, Reprioritizing Enumeration for Property-Based Testing. So, property-based testing, heard a lot about it, well-known, well-loved. What really goes into it? Well, you got property specification, and then to add to that, you have to come up with some form of input generation. And not written here, but you can also do shrinking if you want. Okay, here's an example of a specified property. Let's say we're talking about some version of the lambda calculus with some typing rules, et cetera, et cetera. We have preservation here, a function from a term to Booleans. And what it says is, supposing that we have some term E that's well-typed, if it is well-typed, then its type will be maintained after a single execution step. So let me just walk you through the order of this talk. First things first, I'm going to set up the precondition problem for random generation. I'm going to explain how currently black box random generation doesn't really solve that too easily with automatic methods, but that we can alternatively use lazy enumeration to fix it. Unfortunately, that'll hit an issue. It'll create something called a structural rabbit hole that we'll have to deal with. The remainder of the talk will show you how we attempted to solve these structural rabbit holes and maintain diversity in our search strategy. And then we evaluate on system F. So there are two main approaches to generation. You have randomness and you have enumeration. Starting with randomness. How do we do it? Well, let's first lay out a very simple lambda calculus. We have abstractions, applications, variables, and constants. Notably, we have a nat, which let's just treat as a type synonym for integers under variables here. Why do we have that? Well, we're using De Bruijn indices. How do we randomly generate these terms? Well, in QuickCheck, all you have to do is create an instance of this arbitrary type class. And that means you have to create something of type genTerm. How do you do that? Well, first things first, suppose that we already have an arbitrary instance. Suppose we already have an arbitrary generator for terms. Let's build it up recursively. Just to give a few examples, starting for the generator for constants, all you have to do, take the const constructor and map it over an arbitrary generator for integers, but that's just included in the library for QuickCheck. For something more interesting, a recursive term, we have a generator for applications. We just use applicatives to take the app constructor and map it over two generators for terms. Notably, we assumed we had an arbitrary generator for terms. Stick these all together, and voila, you combining with the one-of combinator to take a uniform selection over all of these, you get something that you can probably just derive automatically. How great is this? Well, maybe it's really good, well, but it might have a little bit of an issue. In particular, with this precondition, well-typedness. The trouble with preconditions is that when you have a random generator that spits out a term that does not satisfy your precondition, you have to discard it. Let's talk about this problem with preconditions. With a very sparse precondition, where most of the terms that you generate will not satisfy the precondition, you're not going to get a lot of good coverage in a decent amount of time running the generator. Let's see if well-typedness suffers from this. So here I'm extending our simple lambda calculus to system F, adding type level lambdas and conditionals and some constants. And I'm going to compare the number of terms that are well-typed to ill-typed, for starting from those that take a single constructor to build. And on the right, those are ill-typed. Remember, we're using De Bruijn indices, and those are either free. The left is a free variable, and the right is just not a natural number. So 2 constructors, that's good, about parity. 3 constructors, oh no, not so good anymore, but hopefully it doesn't get any worse. Here's 4 constructors, here's the well-typed terms. It's probably fine, probably. Oh God, not fine. And it only gets worse. Here's how worse it gets. In fact, if you take the ratio of ill-typed to well-typed terms by constructor count, you get a beautiful exponential 2 to the n. Ooh, wonderful. So you got to ask yourself, do you feel lucky? Do you? I don't. So maybe there's another way. Maybe we can create a generator that comes up with only well-typed terms. That's groovy. People dig it. People have done it. It's not really easy though. Not something you really want to do if you don't want to get distracted for a bit. Here's 3 papers that do it for simply typed lambda calculus, system F, and simply typed lambda calculus with effects. But the trouble is, for preconditions like well-typedness, and there are way more complicated preconditions, it takes a lot of time and effort to come up with an appropriate random generator that really satisfies it. Maybe there's another way, and there is. Enumerations, hip and with it. If it's small, do it all. That is the motto. So the idea for enumeration generation is that all we're going to do is list out all of the values of our data type from small to big, try them out one by one, see what comes out. If we find a violation of our property, hallelujah. How do we do it though? Because we know about enums, but how do you enumerate infinite types? Very simple. Here is an enumerator for our term type. You can see that it mirrors very closely the simple automated generator for random generator. And what does it do? Here is an example of the start of enumeration of the type of lists of integers. See, we start with the empty list, and then we grow to bigger and bigger lists that take either higher valued integers or more or longer lists. And the idea is, if you start small, you'll never miss a small bug.
Is this just enumerating well-typed terms or all terms?
All terms.
All terms.
All terms for now. That was not enumerating terms, though. That was lists. So, does this enumeration fix the precondition problem? No. Well, maybe there's another brand of enumeration we could use. In fact, laziness coming into the picture saves the day, or does it? Here is a partial term. We have a type level lambda, and then an if, and then it has a weird little guard that has a variable that has a negative index. That's ill-typed. We'll come back to that in a second. Both other leaves of this term are undefined. And if you have undefined leaves, well, then you can fill those in with whatever things you want. And here's a couple fulfilled examples, concrete terms, that you can generate from this partial term. We can think of these partial terms as defining sort of an index into a subspace of terms. And in a lazy language like Haskell, if your precondition is lazily evaluated, then you can apply your precondition to a partial term, and maybe you'll get an actual output, if it doesn't care about the undefined portions. Now, this cool little thing, which I didn't come up with, but smart people did, we see that if your term can falsify your precondition while having undefined portions, then the entire space of terms generated by that partial term will also violate your precondition. So if the partial fails, then the entire space fails, and therefore we can discard them all by just looking at a single example. The library lazy search puts this into implementation, and it takes care of our precondition problem. Woo, very nice, by just wiping out discarding all isomorphically failing terms together as one. Here is a bunch of isomorphically ill-typed terms. All of them are just completions of the example that I gave you before, and all of them can be thrown out and discarded by just testing the first one. So, do we have a success yet? Unfortunately, no. So while we can avoid enumerating and trying out all of the ill-typed terms because we discard them all at once, there's these things called that we term rabbit holes, which are the chunks of very similar terms, which are contiguous in the enumeration, that are well-typed and therefore must be ran, each and every one of them. And this is a real chunk of terms that I took out of the enumeration. And you can see how they're all testing pretty much the same behavior because they're all practically the same structure. That's not very good. We want to have a diverse range of behavior being tested. Testing rabbit holes exhaustively is unproductive. How do we avoid staying in these rabbit holes? Well, we're going to try fighting fire with fire. We're going to try using the rabbit holes to fight the rabbit holes. How do we do this? Well, the general strategy is as such. First, we're going to split up our entire input space into smaller subspaces, smaller rabbit holes, which are defined by those prefixes, by those term prefixes, partial terms. We're going to select them one by one, test terms only of that form until some timeout, and then keep looping until we find a counterexample. How do we do this? Well, let's start with the left. How do we generate a structurally similar subspace? Okay. Well, here's a data type that's going to help us out. Index is just a data type that contains very suggestive names, which are the labels of the constructors of our term data type. And we're going to call a pattern a list of these indices. These patterns are going to represent similar subspaces. Okay, here's an example pattern, app prime, abs prime. And one of the partial terms, and therefore subspaces, that it refers to is this one. We have app at the root, and then because we have app prime as the next portion of the pattern, we have app as its child, and then we have abs prime, so the child of that app needs to have an abs, and every other portion of that term is left undefined. See how it defines a path inside of the term. Now, that wasn't the only option. This pattern is associated with 4 different subspaces that are related. It's just choosing where do you put the apps and where do you put the abs. Which children do you choose? So, that's great. We split up our search space, but the trouble is there are a whole lot of subspaces that we've created. In fact, if you have V index constructors, then if you take a pattern of length, or fineness as we term it, F, then there are V to the F different subspaces that we'll have to explore. Ugh, not very good. Can we cut down this search space in a principled manner? I say yes. How do we do it? Well, first things first, we're going to bring in this technique called combinatorial coverage, which is traditionally applied to finite Boolean configurations and how you test those. So let's give an example with that. Naturally, the natural example, we're going to talk about testing a hydraulic switch box with all of the usual Boolean switches. We have front, back, left side, right side, pancake, seesaw, etc., all natural. Can we test all possible configurations, switching these on and off? Well, you could, but it would take 2 to the 10 tests. That's a lot, and maybe we don't want to spend the entire afternoon doing that. So, can we do less? Can we scale down sensibly? Yeah, sure. Let's talk about combinatorial coverage to do so. So instead of testing every possible combination of all the different variables, what if we consider exhausting only exhausting 2-strength or 3-strength interactions, i.e. exhausting subsets of the variables? So here, we consider all of these pairs of the variables, and for each of these pairs, there are 4 possible evaluations of them. True, true, false, 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 true, and true, false. You could also group them by 3 and exhaust all triples. If you do that, then you need 8 tests per triple. That sounds worse. Luckily, because each T-strength interaction has V to the T possible evaluations. But luckily, we can combine them all and pack many interactions into a single test. Here is an example of a generated test for our hydraulic doohickey. Notice that we have circled in red, yellow, and green those same circles that we had on the box. And if you notice, there is for each one of these circled groups, you get a full all 8 possible evaluations of that group. In fact, in general, you reduce your V to the n rows required down to V to the t log n to have combinatorial coverage if you have an interaction strength of 3, meaning you care about subsets of an interaction strength of t, meaning you care about subsets of size t. Okay, but that works on finite sets, okay? How do we extend that to algebraic data types, which are quite infinite? Well, here's the idea. We're going to explore the space of subspaces in a principled fashion by combinatorially covering not the data type itself, but the constructor indices in the patterns that we chop the data type up with. Okay, here's an example of such a combinatorial covering array for patterns. Each row in this array, you can see, represents a sequence of indices and therefore is a pattern. And if you take, here we have strength 2, so if you look at any pair of depths inside this pattern, you will get every single combination of constructor indices. So to give you an example, the top row, abs prime, abs prime, app prime, app prime, is going to be associated with this pattern where we have an abs, abs, app, and then an app as a path through this tree. Okay, so we can select a new subspace. How do we test terms only of that form until a timeout? Well, That's very simple. Let's just take it back to lazy search. Lazy search is very good at dealing with structural preconditions. And all we have to do, if we want to look at terms only of a certain form that match a structural precondition, i.e. this member pattern, all we have to do is just discard all terms that violate the pattern. Very simple. So here is an example on how this member function, which defines our precondition, our structural precondition, works on the app prime index. All we do is we pattern match and look for the app constructor. If it matches, then we take the remainder of the pattern and look for it in the children, either of the children of the app constructor. And it works the same for everything else. So we can now focus our search in the data type by simply conjoining our member pattern to our well-typedness precondition, and then running lazy search. Okay, but then how do you get the patterns? Very simple. We can rely on previously used tools. ACTS is the best thing that I know of for creating combinatorial coverage arrays. So we just make a call to ACTS to make a covering array with a given choice of fineness, i.e. the length of the pattern we choose, and the strength, which is what subset size we care about for exhausting. And then we have a list of patterns. Then all we do, we call first M to run lazy search on each of these patterns until we find a counterexample. That's great, except for one small thing. Lazy search will run as long as it wants until it finds a counterexample. So all we have to do to fix that, to make sure we test all the patterns we care about, add a time limit. Okay, how do we evaluate this technique? Well, we just apply it to system F. The property that we test is that parallel evaluation of system F matches big step evaluation. We use mutation testing, meaning we have 20 injected bugs that we get from the literature. And then our baseline that we test against is lazy search time to failure for finding each of these 20 bugs. Okay, what do we do? Well, what we do is we take 3 different strategies, 3 different choices of hyperparameters for our technique, and run them concurrently to try and find each of the counterexamples. The 3 strategies we do is we do shallow patterns with medium timeouts and low strength to do an overall shallow search for shallow bugs. We look for deeper bugs with deep patterns, long timeouts, and moderate strength, but that's going to skip some patterns because it doesn't have high enough strength. And then we do a high strength, moderately sized patterns and short timeouts to blitz through all of the different possibilities of patterns, just in case. What do we get? Well, on the bottom here, we have listing all of the different mutants that we care about, all the different bugs that we're injecting. In blue, we have our baseline lazy search, and in orange, we have our technique. And you see, we have, in almost every single instance, we beat lazy search very well. In fact, we get up to a 20-fold speed up in bug finding, which is pretty sweet. You'll notice on the left-hand side, you can't see any bars. That's because those didn't take very long to find. On those, we take a little bit of a hit of efficiency. But those are bounded. They don't take more than a few seconds to find, which is well within the range that we bring the difficult bugs down to. So we take a hit in efficiency in finding easy to find bugs, but we get efficient exploration of the search space. And that is the technique. Any questions?
Really fun talk. Thank you.
Thank you.
So when we wrote Do Judge a Test by Its Cover a while back,
Yeah.
we ran into a problem where in normal combinatorial coverage, there are kind of principled ways to know the strength you'll need, just based on statistics that folks have about the kinds of algorithms that they're testing. In this case, it's not really clear, or at least when we were doing it, wasn't clear what the interaction strength meant. And so it wasn't clear how far you might need to enumerate. Have y'all found anything more to that effect to kind of make a principled decision there?
Yeah, on interpreting what interaction strength really means here.
Yeah.
we really, I mean, we have a rough understanding that it means something about it helps tease out deeper bugs, but it's sort of rough. We don't have it's future work to figure it out more concretely. But thank you.
Thank you.
Yeah, I enjoyed reading this paper actually.
Thank you.
But I had a very pragmatic question. It's kind of annoying. We have to call out to an external tool to generate the coverage array.
Yeah.
Do you have any insights in how difficult that would be to just have like a pure Haskell implementation of it? That's the only thing that I thought, this is annoying.
Well, luckily, you asked if there is an easier way than calling out to an external tool. If you have the external tool on your system, then we actually have a very nice Haskell API into it, which we wrote.
Okay, but I still need some...
You do still need the external tool. You could come up with a Haskell implementation of a coverage array generator. But there's just a lot of
how
work
hard
put
it
into
will be.
them.
Oh, it will be difficult?
I mean, that tool has been developed for like decades, so there's a lot of effort being put into there. You could write something simple. You actually don't need that complex of one because, I mean, it doesn't have to be that efficient to come up with the arrays. That's like the smallest part of the testing time that you care about. So yeah, you can write one if you want. We just relied on them because we were actually doing it. We did like a little partnership with NIST, and they came up with that tool.
All right. Thank you.
So each term matches many different patterns.
Yes.
So turning that around, each term may appear in several different enumerations. You may be running the same tests many times. Do you know how often that happens? Is there a problem?
Well, I can tell you that, so that is true, yes. These patterns are a little bit, they overlap somewhat, quite a bit at times. And that might be an issue. We do have some inefficiencies in that, and we actually could have done a couple optimizations there. But we wanted to keep things simple for the user to deal with and keep it sort of uniform. And as a result, I mean, we still have very good performance. So we could have better performance, but that's something that we can consider for the future.
So this is a bit of an abstract question related to the T-strength
Yes.
thing. Do you think if you had like an upper bound of the Kolmogorov complexity of the program you're testing, and then using the T-strength interactions, get like a lower bound of all the behavior the program that you've seen, and then if like the lower bound is bigger than the upper bound, you've kind of seen all the possible kind of interesting behavior, and then kind of get a proof that you've seen everything you wanted to see, or you've seen a good amount of what you wanted to see to get. Do you think that'd be possible?
I think that's a very rad idea. Maybe, I'm not sure. But that's definitely something to try. Thank you.
Thanks.
We have any other questions? We do.
Just related to the patterns or terms matching multiple patterns.
Yeah.
So another option that you could have done would be to have the patterns index which direction the pattern continues on for the branching terms. And I was just wondering if there is some kind of trade-off there, or why you decided to make them more generic just on the constructors.
In the presentation, I showed them just generically based on the constructors. But it's actually you can even do that generically based on the constructors. Just create one pattern for each direction, for each child it could go down, and then you can sort of simplify it, and therefore limit it to one subspace per pattern. And we did that actually. That's one of the strategies we used in the evaluation, and it helps sometimes.
All right, with that, let's thank our speaker one more time. We are now switching over to lightning talks. So Arnold Spivak is going to give our first lightning talk. If you are also doing lightning talks next, come on up. I believe we have five. So I'm going to try keeping us pretty closely to 5 minutes when we're doing that, and you feel free to go ahead and set up. And if you're coming next, let me know.
Who's next?
Who is next? Nikki, who's next?
So May need to do. I'm already there. I seem to. Okay. I need to mirror displays, I think. Absolutely. What? Or I'll have to do it blind, which is going to be very interesting if I have to do that. Okay, it's not opening. So where am I? Here. This is going to be hilarious. It needs to be. It's about the right size. Okay. Come again? I still haven't heard it. I don't hear. I can't hear the question.
Is it night mode? Is that what you're talking
Oh, it is night mode. I can remove it. Yeah. Yeah, because it's I didn't change the time zone, so here we go. Is that better? Oh, that's much better. Yay. I'll be happy, but I don't see my screen, so it's going to be interesting because I'm presenting off a. I don't have slides. I'm just presenting off an Emacs buffer, which is very talkative today. Okay, hello. We get started, I guess. Yes. Okay. So this is a lightning talk that had the fortunate happenstance of having just gotten a 1 hour introduction. So I want to think back about the 2 talks we just had. And they were about property-based testing, but they didn't really talk about properties all that much. They talked about generators and shrinkers, right? Because properties are pretty much always the same all the time. They're not very different. And you have like a gazillion libraries, and they differ by generators and shrinkers. I'm going mostly to speak about random generators in this talk and shrinking, because that's the bit I know best. But I don't think what I'm going to talk about is particular to randomness, and enumerative testing probably works there too. Though I haven't thought about it, so I may be wrong. The problem I have with all that is that these probably like about 15 testing libraries that we have in Haskell all define a property type. Despite the fact that it's always the same thing, ish. And the thing it is IO unit most of the time. Plus some stuff. The fluff around the IU unit is important, but the main technical content is IU unit, and you interpret return as success and exceptions as failures. And that's what a property is, and then there's a good number of ways to build properties. If you think about it, it's not really like super surprising. IO unit is the type of Haskell program, so IO unit is like the maximally powerful type. You can do everything you want with it. And the minimally observable type, you don't know anything about it. That's why you need some stuff on the side very often. And then you have some kind of monad to generate choices, and then you have a for all constructor that says, well, if I have a property that depends on a particular value, then I can generate values for that property and test it. And then your test thing will maybe run the properties 100 times or something like that if it's to test them on various values. Yeah, so the monad probably needs to be an IO monad and stuff like that. It doesn't matter for today. And maybe it's not really IO of unit. Maybe you need more context. But that's the base of the story. By the way, this I can compile this buffer. It's a real Haskell buffer, but it doesn't run anything. And don't obviously. So my point is, I can make a type of generator. I'll put that well in the middle. I typed it E. Fantastic. Okay. So I can make a type of generator that contains all the generators for all the libraries. So these libraries exist. They have different kinds of generators for a good reason. They're constrained in certain ways so that they can combine nicely. That was the whole point of Edsko's talk earlier. So when you inject in this type, you will not have very good combination properties. So you don't really want to use this type all that much. But you can use this type to define the for all combinator that we just saw earlier. And so what we're saying here is there's an existentially quantified x here. So there's some internal state. We can generate stuff of this internal state, and we can show it as an A because we want to generate A, or we can shrink it to smaller x's. And that's all, plus everything you need for display, printing, because you want to show your counterexample, so of course you need a way to print the A's and stuff like that, of course. And these are, the niceties are the important bit, and I'm just focusing on the technical part there. So just as a demonstration, I'm going to take all three favorite libraries of random testing and show how they can inject. So in type check, you have a type class. It's completely, it's not important, but I decided to use the type class nonetheless. You have some monad. Here I just fixed a random monad that I call genm that generates to an A, and then when you have an A, like we have a list, you can make a smaller list by removing the first element, for instance. That's kind of how it works. Or you can remove any element and make a smaller list. That's the general idea. Well, can make a generator. Generators generate directly A, so displaying or passing an A is just the identity. It's already there, and the shrinker, well, the shrinker is just given above. So it works. I should say something about gen. So if you are familiar with imperative encodings, or well, it's just the type of an unfold, basically, right? It will differ because of the nicety. So you could come up with a data structure. It's a nice exercise that a co-inductive data structure that would avoid the existential quantification. But I think it's just easier to use it that way. Anyway, hedgehog is completely misaligned. Ooh, yeah, thanks delay. Okay, we can almost see something here. Here we go. I hope you can all see. Maybe I centered a bit low. Isn't this better? Yeah, maybe. Hedgehog, we saw the type for hedgehog. It's over there too. I have 1 minute. Okay, well, it's good. So these are trees. In that case, the internal state is tree. So you generate trees, and the shrinkers is just passing the tree, and then we have Gumgan, falsify here, sorry, that just, you generate a sample tree, the internal state, the X is the sample tree, and you iterate on it. And then you can implement for all. And so you could implement for all of these libraries directly as well, because it's covariant. So I have, I'm done with my slides-ish. So I'm going to conclude by saying that this talk is less a talk than a call for action. I will not be implementing this. I think Haskell needs a library of property that is generic and can use the properties for every other libraries. There's a lot of thoughts to be put into it to have good UX, have good error reporting in case of failures, and to actually support all libraries. For example, Hedgehog over there was a simplified model of Hedgehog. Hedgehog does mutations, or well, not mutations, effects in many, many places, and you'll have to be able to take care of that. This is not an obstacle, it just makes the model less simple, and you have to care about that. I am happy to advise or to help out anyone who would take this particular task up. So you can come and see me, I'm here until lunch-ish, otherwise you can find me online, and
thank you.
Yeah.
We can take one question as we're changing over the setups, but no more than that. Harry.
I'm curious if you've seen the infrastructure that we built into Etna, the PBT evaluation framework that was presented earlier this week.
No.
Okay, we should chat offline.
Thanks.
All right. Thank you very much. Our next speaker will be Armando Ramirez from Mercury. And just a reminder for everybody, I'm going to be flashing like time signals at you. So we're going to try to keep it to 5 minutes because we have 5 people who want to give talks and about exactly enough time to do that. So please try to keep to your 5-minute slots. Once this goes up. Yes, sorry, and Joachim is next. Then you.
Is it not working? Oh wait, let's mirror.
There we go. Let's see, can you hear me? Can you hear me? Okay. Okay, so I'm Armando Ramirez. I'm a Haskell engineer at Mercury. I also do some Haskell game dev on the side. And I'm going to go over just 2 fun tricks to help you guide inference when you're doing some kind of weird, advanced typey stuff. So what's one situation where type inference fails? And a classic example is when you have some sort of multi-param type class, you have some sort of polymorphic usage of it, and then you get poor inference. So what does that look like? Basically, GHC can't figure out what that R parameter to monad reader is, because length is polymorphic in the foldable, polymorphic in the A. So this happens in a lot of situations. Function composition, overload, records labels. Now, for this specific example, I'm aware you could just slap a fund up on it, call it a day. But you can't actually always do that. For instance, if you're using extensible effects, and you have a reader in your effects stack, maybe you have 2, maybe you have 1. If you build this, you also get an issue due to ambiguity, whether you have 1 in there, or you write polymorphically over the list. You also get it. Now, when you're polymorphic over the list, it's fair for there not to be, for inference to fail, because there could be 2 in the list. But in this case of no inference, when the concrete list, like I'm staring at the 1 reader, why can't GHC find it? So let's give it some help. And let's prove to GHC that there is 1 in the list. So in this case, this is kind of the API. We say that there is the effect in the list. So you have this is the higher kind of effect, like reader. This A is the parameter, like R. And this is the list of effects that we're searching. And then all you do is you just, instead of having a member constraint, you have a the constraint. So you say in this list, there is 1 reader, and the reader has a type of R. And then you just have as the, and then it just works. And then down here is just all the guts, the type level guts of just traversing the list, making sure there's not duplicates, making sure there's not duplicates, both literal duplicates and 2 readers of different types. And you get nice type errors for that. So let's see this work. So here's basically the same program as before. I just replaced asks with asks the. And it builds. And it also works when you just bring the constraint in yourself. And just to show off the fancy type errors, you do get yelled at if you have a duplicate, and you actually don't have like a canonical thing in there. So this is kind of a way to decouple that fundep from the type class, and you can kind of bring it on a la carte as you need it. And that's pretty useful. It's useful. I find it useful in effects. I'm using Clef here. But sometimes you do want 2 readers, and depending on your scope, you want one to be the one that that inference is focused on. So I have a way to do that too, and this is a little weirder technique. You basically you can use an implicit param that's a proxy, and it's parametric in R. Now implicit params are always concrete. So basically what happens is you just slap that constraint on there, and then when you call this, that R is fixed, and then that helps guide GHC to find the reader that you're looking for. And I have this with imp reader just so you don't have to use, it's not nice to use implicit params directly, but it's not bad this way. So here's a simple way to use it. Here we have 2 readers. We do with imp reader, then in this block, everything will be guided towards the reader of list of ints. In here, it's guided towards strings. This program works. I think it's not as useful for this, but say you had you could put a do block in there with state. You have multiple states focusing on them. I can imagine this being useful for just if you have something very type levelly, type directed, and you need some UX stuff so your users can not put 10 type applications at every use site, but just 1 type application that goes to the block. So that's it. Those are the 2 tricks. They were meant to be fun, but also useful. And if you want to look at the code, it's on my GitHub, Ramirez7. Thank you. Thank you very much. Once again, we've got time for a question as things change over. And if not, no, it's just on a gist. But I could. It's just I can release the Oh, and the one I guess I said out of time. The reason I did this to begin with, there is a GHC plugin for the extensible effects that does this for you. but I was cross-compiling, and it yelled at me for using plugins, so I just had to do it in TypeSpace land. Alas. All right. Our next speaker is Joachim Breitner.
Okay. Who saw my talk on Tuesday? I made a mistake there. I made a claim without testing it. I said this idea can allow you to write a parser combinator library where left recursion works if you have sharing. And I didn't actually try it because it was obvious it would work, but people didn't like that, so more progress. So here's a conventional parser combinator library. I took this code from the Arcta code base. And with these parser combinators, if I write a parser, this is a parser that detects sequences of A's with left recursion. Oh, is this big enough? Probably not. Then if I use this parser, it will just hang. This is the problem with left recursion in parser combinators. Now, this particular library has a memoize operator where I can make the recursion explicit by giving a unique key for this, this rule, and then it works. Now, my claim is I can take these kind of slightly imperative ways where you have to be explicit of recursion, and if you use sharing, it works. So let's read another file. Has this, loaded, and then try this again. So here's the recursive definition with no explicit annotation for the recursive thing, and it works. So how does this work? We can look at the code briefly. This is the module. It is a new type wrapper around the. Is this bigger? It's a new type wrapper around the library. And then, of course, non-recursive combinators I can just wrap normally. And this is all the magic. This is this combinator called proprio sept, which tells a thunk about its own identity. So you can use it to create a thunk that has a unique. And different thunks will have different uniques. And with this, the name basically, of course, is Richard Eisenberg's input. I didn't know about this word before. And I can use this to create a combinator called with memo, which takes one of these underlying combinators and turns in a new combinator with my abstraction that uses the memoize function. And now all the combinators that may possibly be recursive, which in this case are functor, applicative, monad, alternative, I just use with memo, so they know about their uniqueness. And now I can do this thing. And here's a larger example. Okay, I'll also make the font larger, so that the example is even larger. A simple data type for grammars, and now a grammar to parse BNF syntax. And there's some left recursion here. I mean, I don't look at the details, but here BNF is left recursive in BNF. And let's try to use this. So I can now try to parse this. Okay, I'm now using this BNF parser that I defined. Sorry, wrong window. On this BNF syntax here. So a BNF for numerical expressions, and it doesn't work. This is the not tying trickiness. This is a left recursive definition that doesn't do sharing. It's like a lexeme combinator. You see it calls LP itself, but it's not sharing. But I can make this. I can use the usual just when you do not tying in Haskell normally, you make sure that the recursion goes through a local let definition. And if I now reload, this works, and I can parse this thing using left recursion grammar. And of course, the benefit of having a parser combinator is I can now use it dynamically. So I can, for some reason, I just parsed a BNF grammar. So I can interpret that data structure now into a grammar. And again, the grammar that I just defined is left recursive all over the place. But because my interpretation is careful to be cyclic, it's using this map of parsers, and it's using them below, I can now take this BNF description, interpret it, and then parse expressions with it, even though it's left recursive. Oh, I have 30 more seconds, but I'm done. So you can go over. There are 2 questions.
Yes, as is a tradition.
So there's a reason why unsafe perform IO is called unsafe perform IO.
Thank you.
And
Yes.
yet you're using it in some kind of safe way. Can you think of some kind of primitive operation you could end up making a respectable, reasonable about thing?
Well, I think there's always going to be some layer where you have to. So in this case, I think the code here is using unsafeness, but then the API I provide will be safe again. The argument here is, which I haven't verified because I haven't written the library below, that it doesn't matter to the memorize function, to the underlying parser, if you, like what the precise key is you pass there and you can't observe that, and then it becomes safe again.
Let's talk about the laptops.
Yeah, so go ahead.
And also, the next person I can't read my own handwriting, but your name begins with an L. Okay, there's only one other person who I think has to do this, so please come up. Okay, any? No. You're good. Yeah, okay.
No more questions? Good.
Richard does need the mic.
I can try to do PowerPoint.
He is pretty loud, but for the general benefit. So yes, our next speaker will be Richard Eisenberg.
Okay, is the mic picking me up?
Sure is.
Yes, and the video is picking me up too. Good, okay. So I just wanted to share a little bit of work I'm doing because it might be of interest in the lightning talk, so why not? This is ticket 23162, which is a small improvement to the inference around closed type families. I don't have a full motivation here up on the screen, but the actual motivation is there was some proposal that introduced names for all of the tuples, and there was some grand type family that counted up to 64 and figured out exactly what tuple you mean given a number, but it turned out that the inference around that was bad. So I thought, let's just improve inference. So let's say we have a type family like this, TF, and note that TF is not injective. There are two different arguments, int and double, which both map to car. But actually, if we know that the result is this one here, then we can actually infer, we know that the argument has to be bool. And I have some function f. Obviously, we can't define f, but maybe there's a class constraint or something that would allow us to define it. In general, you can. But then I want to look down at here. If we have G, bigger. Okay, is that better? Yes, good. Okay. So G is just a call of f, and but it doesn't do it. What it does is it constrains that the result of f is a maybe of something. It doesn't even. It's not even necessarily maybe integer, but we know that the result has to be a maybe something. So right now, if I try to infer the type here, I can say GHCI of this thing and ask what is the type of G, and we get this. It works. GHC can infer this, but it gives me this big type and says, okay, the result of TF has to be a maybe, and the original thing has to be showable, and that's kind of a pain. In the actual motivating example, it doesn't even compile because things are just much more complicated, and there's like a class constraint that can't get solved. If I use my development branch here, build, what do I have to say, stage 1, bin GHC interactive of lightning, blah. Okay, so now it loads, and now the type of G is this nice bool arrow string, right? Because it uses the fact that TF is closed to say, well, if the result is maybe, then there's just only one way to have done that, and it has to be bool, and why are we messing around with anything else? Unfortunately, not all is well. And this means I have to redesign how functional dependencies work in general. You pull on one little piece of string and then the whole thing unravels. So here I took that type signature that GHCI reported back to me, and I put it here. It's the same type signature. The only thing I've done is I've had to add this call to this silly type function id, and that's just to confound the type checker. The type checker is clever enough, if I don't put the id in here, then the effect that I'm looking for won't happen. But now, if I try to reload, it fails, saying that the type of H is ambiguous because it can't, let's see, I probably don't have quite enough time to explain exactly why. There's a lot going on here. The problem is that this constraint here doesn't, in GHC's telling, does not tell me that A1 has to be bool. I don't get a given from this constraint that I can then use to prove that A1 equals bool. I can only sort of infer it. And the solution is going to be wait to do functional dependencies later. I can say more in the break. But in any case, I thought this was kind of fun and wanted to share. That's it.
All right, once again, while we're switching up, you feel free to ask questions.
What happens if there are two cases matching, but not all of them? Do you get a disjunction of things?
No.
Can we have it?
It's just you don't make any progress. I mean, although if you had maybe bool and maybe integer as two different possible results, and there was something similar about the arguments, it would be able to infer that.
Oh, nice. Thanks.
I think. Sounds plausible.
And our final speaker for the lightning talk session is Laute Stegeman, who will be talking to us about this.
Okay, thank you. And thank you for pronouncing my name pretty close to the correct pronunciation. Okay, so this ICFP, I've been getting a few questions about GHCDS, whether it's dead or not, and some people don't know about the GHC JavaScript backend, so I'm going to give a brief introduction, say what the status is. Briefly, it's the GHC backend for JavaScript. Everything has been integrated into GHC. It uses the Haskell to core to STG to JavaScript pipeline. There's no CMM involved. We depend on mscripton and Node.js, but mscripton is mostly used for basic toolchain things. We don't really support compiling C sources directly to JavaScript. A bit of glue is needed if you actually want to use mscripton compiled sources. It's based on GHCDS. We fixed a lot of things. Everything is built with tested with the GHC test suite now. We found a lot of things and it's improved, but also a lot faster. But some things are still missing. If you're used to GHCDS, then optimizer is missing. You still get bigger executables. We're working on that. Incremental linking is missing, splitting your executable into multiple things, and the convenient JavaScript or the convenient foreign import syntax with the $1, $2 placeholders is still missing, but basic syntax works, so it's very easy to convert things over. So why are we doing this? Well, the original motivation was to build, to make Haskell accessible in browsers, and also scripting on Node.js compiles something that you can just deploy everywhere else. Everything is bundled, and you can use it instead of shell scripting with nicer type safety and stuff. Also, I'm interested in finding out what the kind of things we need from Haskell in a managed runtime. If we don't do bit manipulation and are a bit higher level, what features do we need? For example, we have special weak references, ephemerons, and we can often get away with simpler things. And for example, from the WASM people, we had the questions a couple of times, like what kind of features do we need from a garbage collector or for fast pattern matching? So really the JavaScript pipeline is a pipeline for a managed runtime, where maybe we can use these kind of things in the future to answer these questions and experiment with it. Another thing that I really like for being a sort of higher level output for GHC is that we can often use the JavaScript or V8 tools to inspect the heap and to get more information about our Haskell programs. It's much more, I get less headaches using V8 and the graphical tools to inspect what my Haskell program is doing than using GDB or LLDB. So I hope we can at least keep it alive for that kind of things. So where are we? In 9.6, everything was integrated, was merged. We could do Cabal simple install, but not the custom scripts. And we didn't have template Haskell. Those were fixed in GHC 9.8. So most things you could install with GHCDS, you could now install with the backend. Later we'll get the optimizer and profiling and better FFI. But let me get a quick introduction of some things where you might be able to help. If you have packages that work with Haskell and you have some C sources, some things that are not Haskell, then you might, to get them supported with this backend, write a bit of JavaScript. You can use the Cabal flags that test for the JavaScript architecture and add your JavaScript files to your package and write a bit of JavaScript glue code that yeah, just does the work of the non-Haskell code in the existing packages. So for simple examples, if we have, say, a function, a memcomp function, which takes 2 pointers and a number, and we check whether the one of the memory regions is bigger or smaller than the other. Pointers are represented as pairs. AV and AO are A value, A offset, BV, B offset. There's a bit of data structures involved that are not very complicated, and usually it's there's a bit of manual work involved in converting it, but it's fairly straightforward to convert existing C code to JavaScript code that works with a different memory representation. Sometimes there might be more specific things like Node.js. You can do scripting, do processes that aren't available everywhere. We have some utilities to help with decoding, convert from Haskell C strings that are pointers to JavaScript strings, and platform detection for features that might not be available on all platforms. So if you want to help, then it's nowadays very easy to install. This was a hard question or uncomfortable question, but you can. These 3 lines are enough. You need Emscripten. After you configure your GHC, you can build it with Hadrian, and then you can use Node.js just to test the generated JavaScript. You can also use GHC up and Haskell.nix. Haskell.nix is useful for CI. There are some things involved, a few more steps to activate the right testing repositories, but it's really quite easy to install. And if you have something that, oops, that's the last thing of my slide and also the last second. If there's something broken, then please tell us. It's easy to test now. So thanks.
Thank you. There's one quick question. We have time for exactly one quick question.
So is there any plan to have some sort of FFI for C, like C to JavaScript or Emscripten? Because certain libraries do, like SDO2, how to JavaScript, and it'd be nice to be able to just understand how it is.
The question is there a way to do FFI to C from JavaScript? Just to, yes?
C compiled to JavaScript.
C compiled
Yes.
to JavaScript.
It is. It's already possible, but since we have a different representation of our memory, all the C is compiled to something where pointers are all pointing to the same buffer. And with our managed memory, where all the Haskell heap objects are separate objects and stuff, we support multiple buffers. So there's a slight impedance mismatch, but usually it's very easy to write a few lines of glue code between the Haskell code and the C code. And we've done that for IOG with crypto libraries. So, yeah.
Thank you. Let's thank all our speakers one more time. And the session is now over, so let's all eat some lunch finally.
Oh, an excellent. Two? Okay. Oh, they're actually good. So a couple of people have videos. Oh, All right. Can everyone hear me okay? Just. All right. Can everyone hear me okay? Okay, there we go. All right. Hi, everyone. My name is Aaron Allen. I'm on the Haskell.org committee. I also write Haskell professionally for a company called HEB. So, as you may know, Haskell has a long-standing and successful presence in the Google Summer of Code program. Unfortunately, this year we weren't accepted into Google Summer of Code, but we wanted to keep that momentum going from previous years, so the Summer of Haskell 2023 was born. And I'd also like to give a shout out to David Christensen, Gershom Baserman, and Jasper Van Schut for assisting in organizing and running this event. And a huge thank you to the sponsors who provided financial backing that made this possible. So here we have a list of all of the participants. So each contributor has a project and a mentor that they worked with in order to hack on something that would provide benefit to the ecosystem. And the bulk of this presentation is going to be the contributors explaining their projects and showing some of the results. So without further ado, let's get into that. First up, we have Ben Bellick.
Hear me? Cool. All right, so today I'm talking about rendering GHC diagnostics as JSON. As Aaron just said, I'm Ben Bellick. It's just a little bit about me. I got selected for Summer of Haskell. I was really excited to contribute to GHC this summer, so this has been a great opportunity for myself. So let's get started. So today I'm talking about a new feature that I'm trying to help bring to GHC, which is a flag that helps make GHC's diagnostics more easily readable by a machine. So to put this in another way, let's make GHC's diagnostics available for everyone, regardless of what platform, what tools they're using. We should make sure it's easy to consume. So let's see an example just to get a flavor of what this particular flag is going to do. So this is, I'm sure, recognizable to everyone, an error output by GHC. And you can see it's got a lot of great info inside of it, but it's a terrible pain to parse by hand. And to make matters worse, the actual output can change between releases. So for example, some people might be familiar with, can you see, yeah, with this code here, and some people might not. It's something that's being rolled out in real time to basically add error codes to all the possible errors to GHC. If you wrote a tool that was parsing this information by hand and suddenly that came up in a new release, boom, that's a big issue, right? All of a sudden you have to rewrite your parser by hand again. So how can we make this easier for people to consume? We represent it as JSON. So now all of the information that you actually want is available in its own individual field. And this is hugely beneficial because now who cares if a new field pops up when you're not expecting one, as long as this format stays consistent. So why do we care about doing this? As I just mentioned, it makes the tool available for everyone. So I think everyone realizes that right now, the state of Haskell tooling, there's a huge amount of dependence between GHC and all the subsequent tooling. All the tooling basically uses GHC as a library to get things like the abstract syntax tree, et cetera. And this is great because people get a lot of things for free. But it would also be great if there was a way to decouple these two things and make these things available to people who don't want to actually tap into GHC as a library. And then the other benefit is generally just to let people take advantage of this new motion to represent errors as structured values. So for those of you who are GHC contributors, you might be familiar with what this means, but just to touch on it very briefly, in the old versions of GHC, errors basically used to get passed around as a type called sdocs, which you can really just think about as strings. Essentially, at the call site, a string was produced that described the error, and then it got passed up, which is very easy, to just do and make new errors willy-nilly whenever you want. But it creates a big problem for actually creating sophisticated Haskell language tools, right? Because that means a lot of people are having to parse these strings by hand to figure out things like which variable triggered this issue, et cetera. So basically, we want to make these errors as useful to people as possible. And so there's been this motion underway to represent errors as structured values, basically. So you can think about that basically like instead of passing a string around, you've got a sum type that represents all the different possible error cases, and each one has its own constructor whose parameters are the values of note, basically, in the actual error. So just to give you an example of what it looks like now, this is like almost all of the code I actually have in this presentation. But so this is the current implementation of errors in GHC, now with this new errors as values paradigm. And the details don't really matter. This particular E here is something that generally is going to be an instance of type diagnostic, which is this class. So basically, you can see now getting passed around all throughout the compiler is all of this information separated out, right? You can separately grab diagnostic codes, the diagnostic reason, the message. All of these individual pieces of information are not just one single string, but are available to people who are actually tapping into GHC as an API. So now that you see that, it maybe becomes a little bit more apparent why there's a benefit to actually expressing these constructs in something other than GHC's API. We want to make them available to people who don't want to have to tap into GHC's API and instead just make them available to anyone that wants to write a tool in any language, whether it's Python or JavaScript or anything. So just a quick acknowledgement. There is actually a flag in GHC right now that does more or less do something similar. Maybe it looks familiar to some of you. It's this dedump JSON. And this flag is useful, but its usefulness is actually quite limited as it stands right now. So on the one hand, the way things stand right now is it's a little underspecified. So you can actually look at some of these details and you see that you're getting the same JSON structure out for a compiling message and also for a diagnostic message when these are clearly two different things. Additionally, you can see that in the message class field right here, there's a ton of good information, right? I mean, it's got the error code, it's got the message class, it's got the severity of the error, and it also has this just parameter. What does that mean? I'm not sure. But the point is, if it's not obvious to me that's been working on this, it's definitely not obvious to someone who's been working on the code base trying to develop tools. So how can we make this info more easily grabbable, more obvious what it does? So how do we do that? There's a new flag, fdiagnostics as JSON, that basically produces all of the error messages as single lines of diagnostic messages represented in JSON. And then additionally, we have a JSON schema that basically formalizes the exact contract of what you can expect to come out from each of these diagnostics. So this schema is really an important thing because it makes it explicit to users what exactly they can expect to come out of this flag. So JSON schemas is a particular concept that maybe not everyone's familiar with. I don't want to spend too much time on it, but it's kind of what it sounds like. We want a way to basically inform users that there's some constraints that all of these outputs are going to satisfy. And so this is extremely useful because it lets people expect consistent outputs from GHC, and when there's a change, they can actually go check the schema to understand the change that's been made. So we'll see an example here of a little bit of a JSON schema, but if you're actually interested in learning more about it, it's here. It's got lots of different bits of, like nomenclature and whatever, but the details aren't important. The idea is really just this, right? if you are a developer of a GHC tool, now you can look at this schema and see, oh, I know that only warning or error will be reported in the severity field. And I know that codes can be null or can be integers. And the reason why they can't be null is a variety of reasons. Some errors don't have integers assigned yet, and some errors are the result of plugins. But regardless, now you can make much more informed decisions about what you can actually expect to come out of this diagnostic message. So the current state of things is that there's a merge request open. I think it looks okay. I've actually gotten some feedback from some people in the audience here, which I appreciate a lot. But it's not merged in, and I think that there probably are people here that would benefit from such a feature. And so if you are one of those people, now, or I guess not like right now, but now in a general sense is a great time to give any feedback at all about things that you wish it had, things that you wish it didn't have, etc. So the flag is fdiagnostics as JSON. This is what error messages look like now, and here's what they look like with the flag passed in. It got a little cut off, but I think you understand the spirit of the message. And possible work down the line. Rust's compiler actually also has a JSON output feature, but the difference there is that theirs is actually a little bit more sophisticated and also offers JSON output of all different kinds of output. So compiler messages in addition to actual diagnostic messages. That could be a useful thing down the line, but that would involve a new specification, and so I was trying to keep the scope limited. And then we can also, of course, add more useful information to the JSON diagnostic messages. So yeah, that's my presentation. Happy to take any questions or anything like that. And again, please reach out if you actually have things that you want changed about the flag. It's not merged in. Everyone knows it's much easier to do things right the first time than to fix things after the fact. Yeah, and also just thanks to Aaron Allen for mentoring me through this and the Haskell Foundation for doing this program. Thank you, everyone. All right.
Dominique, are you ready?
Hi, everyone. My name is Dominic Millshowell, and I'm going to talk about the work I've been doing in Summer of Haskell over the past couple of months, specifically with the Improving Calligraphy project. So you're probably, the initial question in your head is probably, what's calligraphy? So calligraphy is a Haskell call graph / source code visualizer. It uses information from the HIE files generated from GHC to produce visualizations. And for the uninitiated, HIE stands for Haskell Interface Extension. They're binary data that's produced from GHC during the build process, and it contains serializable data related to Haskell modules such as type information, metadata, and the like. And this is very useful for developing tooling, more advanced tooling with features such as navigation, code completion, and the like as well. So the benefits of this is manifold. And it's probably the most prominent use of HIE files is within the Haskell language server. And to kind of give you, a clue as to how calligraphy looks like in, its formative stages, this is how I got it handed to me. It's after building with Cabal and getting executable and then adding it to your path, you can target specific modules and it would produce a neat graph like this. Of course, if you don't add any arguments related to specific modules, it would just generate a graph containing all the modules within this project that you specified. And some commentary is necessary here. So the house shape nodes are type classes. The octagonal node is a type constructor or type family or type synonym. The rectangle is, oh, I'm sorry, I got ahead of myself. So, all right, this repository is from Edward Kemet's semigroups library. And the reason I chose that specifically with these two modules is because those encompass the entire possible nodes that calligraphy uses and also all the possible edges that calligraphy uses. So it serves as a good motivating example to explain everything that, it's an exhaustive example, as you could say. And as previously mentioned, the house node is a type class. The octagonal node is a type constructor. The rectangular node is just a regular constructor. The ovals are just values. The rectangular node with the rounded edges are records. And the ovals are just values. And the arrows, there are three types of arrows. There are the solid line arrows, which indicates a relationship from a caller to a callee, meaning that where the end of the arrow was called in the beginning of the arrow, and the perforated lines indicate a parent-child relationship wherein what's usually on top is the parent and what's usually under the bottom is the child. Parent and child here means that the child was introduced somewhere within the body of the parent. And I mean, I know this sounds quite general in a sense, but it's best to describe it this way because it does encompass different types of situations. And for the sake of brevity, it's better not to go into this. But also the dotted lines also indicate the dotted lines indicate typing relationships. So what was used in the type at the end of the dotted line, what's at the end of the dotted line arrow was used in the type of the initial starting point arrow. So from the get-go, if you look at something like this, you can see, it's really useful if you want some information about whatever Haskell project you're working on, but also it's not very interactive. If you have a really huge, large-scale project, it's going to generate this monster of an image in which you really can't discern what's going on. And it would benefit from having some more interactivity. So the goals of this project were twofold. One is to modularize calligraphy into various parts, such as the calligraphy GUI, GraphViz, CLI, and FGL. So FGL is functional graph library. GraphViz is a means to generate graphic type data. And the second point is to ensure that calligraphy keeps up to date with new GHC releases. So I'm going to tackle the second point first. And if anyone's ever maintained a Haskell project or kind of delved into one, you'll notice that it's kind of a struggle to just keep up to date with new GHC releases. You usually have to kind of use some hacky method where you introduce some snippet that says if this GHC version is available, if you're using this current GHC version, then this snippet applies, else this snippet applies. And we need a more sustainable way to kind of address these new changes. And I'm sorry to say that I did not achieve this because GHC is kind of a complex beast. So after spending an inordinate amount of time on this, I've kind of redefined this goal as more of a stretch goal. But funnily enough, I have actually gotten a lot of insight from just attending the symposium. So, I mean, I've gotten a lot of different perspectives, such as like using bidirectional programming, template metaprogramming, and even I hear there's work being done on an API to kind of consolidate various different, differences between different GHC versions. But of course, this is, in its infancy, and it hasn't really reached a point of fruition yet. But the goal itself was, I could say, in a sense, unachievable because of just the complex nature of GHC. But I kind of just want to still talk about some of the issues that are present within the code base now related to this issue that I'm mentioning. So, if you look at the type-related logic, meaning the logic that I just described to this, like how the various edges and nodes are formed, then it's not that much. If you look in the repository, it's just 15 lines of code. And it works in general pretty well, except for some particular exceptions, such as with field accessors in GHC 9.2. And what we usually what we have done is just kind of take an approach where if it works, it works. If it doesn't, it doesn't. Because if it works 90% of the time and it doesn't work 10% of the time, then we're not really going to focus on the 10%. We're going to just focus on the 90%. And another issue is just that it builds with the most recent versions of GHC, but it can't necessarily parse and handle all the call graphs generated from all the GHC versions. Sometimes calligraphy will be nice and error out. Other times, you may just get an incorrect call graph returned. And this is just kind of an overview of my struggles with trying to just work with different approaches to deal with these GHC, these versioning issues. But realistically, it wasn't necessarily feasible to come up with this, so I'm going to talk about the more productive option of the two, which is modularizing calligraphy. So this was the initial goal, to kind of modularize calligraphy into various constituent parts. And the reason for this was hinted at before, where it's unwieldy to just use a CLI. You kind of want something more interactive, and you want something more maintainable if you want to add. Well, also you want to add certain kind of bindings, because right now the logic used for GraphViz and FGL is ad hoc. It doesn't actually delve into the libraries themselves, but rather just particular use cases of what we need to generate a graph that we want. And the issue, as I just said a while ago, the issue lies with designing the GUI currently. So this is not so much an engineering problem as it is a design problem, because we've taken maybe 3 approaches. So one using D3.js, which is the JavaScript library for producing nice visualizations. This works, but it's not very maintainable because JavaScript. And we've also taken an approach using PureScript, which is maintainable but not useful for kind of just coming up with things on the fly, which is, if you want to move fast, I've taken the approach of using GTK+, which works well if you just want to break things fast and figure out why they broke and then try to fix them. And the reason why the graph configuration is kind of challenging is because the design space is quite large. And what I mean by that is that it's large in the sense that if you have a large project, it's going to be large because you generate so many different configurations of disjoint graphs. But also, it's large because the tools that we're using are somewhat underspecified for more complex cases. And that's where the aspects of GraphViz and FGL come in, because how calligraphy works right now is that it builds the GraphViz file by just concatenating text in a very ad hoc fashion, instead of relying on like a more complete solution. So if you want, something more refined, you're going to have to write it yourself and get calligraphy to build it. So in the similar vein, if you want more nuanced algorithms or if you want something like, say, the boundary of a graph, you would probably, you can't get that from the get-go with calligraphy. It'd be much better if we have a more general approach that integrates the FGL library. And, the upshot of this lightweight approach is that it works, it's simple, but, for future use cases, it's better to kind of just have those bindings in place so you can have far more options available to you. So in terms of the work being done, which I probably didn't categorize as in this talk as it would, the CLI is complete, and more or less the bindings have been in place. The issue mainly lies with the GUI, and I actually really struggled to put the GUI on a slide because it's just so unwieldy, like you don't really see anything, you just kind of see some dots that you can vaguely make out, so it didn't really seem necessary. Well, I couldn't figure out a way to put it on the slides themselves, and yeah, that's more or less where we're at. So thanks for your attention.
Greg, you ready?
Okay, this. I'll just hold it, I guess. Sorry. Okay. Hello, everyone. I am Greg. My project is maximally decoupling Haddock and GHC. A bit about me is that I am currently a university student. This is a project that I did. This is my summer project, basically sort of like a summer internship, I guess. Wait. Anyway, so the background for this project: GHC is the compiler for the standard compiler for Haskell. There are others, but this one is pretty much the de facto standard. Likewise, Haddock is the documentation generator for Haskell, which takes a Haskell project and outputs documentation in various formats. One format would be documentation that you can view on Hackage, the package manager, which you can view online. Another format would be for another backend would be for Hugel, which allows you to search for functions via names or type signatures. And the problem is that these two tools have a very GHC and Haddock have a very strong connection between each other. Haddock is strongly coupled to GHC. For instance, the Haskell abstract syntax tree is defined in GHC and used by Haddock. And this is unfortunate. This is largely out of necessity in a way because GHC's syntax tree is very large. It is very unwieldy. However, this is a problem. The abstract syntax tree changes quite frequently, relatively frequently. Every time that, for example, that there is a new language extension, it is often added to the syntax tree. There's also refactoring done internally in GHC for other reasons, and every time that this happens, the types of the syntax tree change, and likewise, and so Haddock has to be changed as well. What problems does this cause? What problems does this linkage cause? For one thing, this means that the version of Haddock that you use is tied to the version of GHC that you're using. This presents a major problem, for example, for tooling such as Hackage, which struggles due to the gap between Haddock versions and GHC, versions, and the large number of GHC versions that are used by packages on Haddock. Some packages are very new, while others may be years or decades old. Another problem is that the development of both GHC and Haddock is slowed due to the need to make sure that both of them are using the same version of the AST. And my proposal for fixing this issue was part of a larger effort to decouple Haddock and GHC, and I proposed the following steps. One of them was designing an intermediate. I proposed these following steps as part of my project. One was to design an intermediate representation, IR, for the Haskell AST and implementing the conversions between the AST and the IR and serialization to and deserialization from disk. Another necessary part was to of course update Haddock and update GHC to interact through the intermediate representation rather than directly sharing the syntax, and then having Haddock get the syntax tree directly from GHC. And another change was to, of course, update the Haddock backends, which currently use the Haskell syntax tree from GHC in order to use a representation which is not imported from GHC. You can read more about this in Haskell Tech Proposal number 44, I believe. And you might ask, why do we need a new intermediate representation? Why not simply use the Haskell syntax that we already have? You can already, of course, serialize it to disk deserialize it by parsing, and you wouldn't need a conversion. And to answer, and I mentioned this because I think it's good to it's good to understand why this would be helpful. One reason is for its compatibility. If future Haskell versions may have new syntax, and they probably will introduce new syntax that is currently unsupported by Haskell, and this of course is a problem. If you tried to parse a modern Haskell project that makes use of some language extensions which introduce new syntax using a much older version of GHC, you would get a parsing error. However, with an intermediate representation, you could enforce a consistent syntax, allowing the parser to at least parse the project and of course, some parts would nonetheless have new bits of syntax, new features which are unsupported by the current version of Haddock. But with those you would be able to identify them and minimize the scope of the impact, perhaps outputting most of all of the bits of documentation they can, except for the very few pieces that depend on those new features. As another advantage is being able to interact with third-party tooling. So a lot of tools may be written that may want to make use of Haskell AST, and not all of them may necessarily be written in Haskell. Some may, for example, be written in Python. These obviously cannot make use of any Haskell libraries for dealing with the Haskell AST. They probably do not have a Haskell parser available. And of course, writing a Haskell parser is especially for a small tool, is going to be very undesirable. Parsing Haskell is currently rather complex, and you don't want to go through all that trouble. Instead, you may use an intermediate representation may be designed so that it is much easier to parse. And in fact, depending on the intermediate representation which is chosen, a parser may be available, quote unquote, out of the box. This brings us to the chosen intermediate representation. It is basically JSON, and this has a few advantages. One is of course that JSON parsers are available out of the box for many languages. Instead of having to write so if you wanted to write, for example, Python tooling to work with Haskell code, you would not have to write a parser. You would simply have to parse the intermediate representation as JSON, and then depending on the language, you could either use the parse result as is, or write some boilerplate to convert it into a statically typed format if you were using a statically typed language. Another advantage of JSON, more so of a requirement really, is that it supports all the features that you would need in order to adequately represent Haskell code. It has strings, it has numbers for primitives, and in order to and JSON arrays and objects provide a convenient mechanism for representing Haskell structures. Features such as records and different constructors in the cases of some types may be encoded through the use of a special label that may be specified in the schema. And so during the work on this project, if we go back, we can see that the original proposal was quite ambitious. Unfortunately, not everything could be accomplished due to several setbacks. One, for example, is the way interoperation between Haddock and GHC works. Haddock, as it currently is, essentially uses a GHC plugin. It goes into, and what this plugin does, it's it's a rather complex thing. It goes into GHC and it not only extracts the syntax tree, but also does some processing on it. And I felt that replacing this plugin would be a technically difficult project, perhaps requiring additional feedback. And so I decided to move this to future work in a way on commentary. Another issue is the broader effort to remove the Haskell AST from GHC. This is currently an ongoing effort. There is work on moving the Haskell syntax tree into a module language.haskell.syntax, which is not part of the quote-unquote GHC core that is problematic to use in Haddock. However, this project is ongoing. Some parts of if you were to actually use language.haskell.syntax, you'd find that there will be some dependencies that are still in core GHC. So unfortunately, as it is, this fully moving away from GHC in the backends cannot be done yet. You may ask why, and of course, why not simply copy the syntax tree? The answer is that, again, it is very large, very complex. You do not want to do this. And ultimately, the final product of this project will be a proposal, which will include the intermediate representation, a prototype which accomplishes conversion between the Haskell AST and the intermediate representation, and of course serialization to and deserialization from disk. This prototype, of course, this prototype will not necessarily be a suitable for use directly in GHC. It probably need to be. It is entirely possible that there will need to be refactoring and optimization done in order to use it. But the point is that it will allow. It will serve as a demonstration that that the intermediate representation does work. There will also be indication of future work that needs to be done. For example, the steps needed to fully integrate this into Haddock and GHC, and of course, room for commentary on how these steps can be taken. And hopefully, the work product of the project may be used to improve Haddock and GHC. If that this proposal should be available in a few weeks, and that would be a perfect time to leave comments on it. And as for acknowledgments, there was already a table of mentors and participants and mentors, but nonetheless I would like to acknowledge my project mentor Laron and the Haskell.org committee for making Summer of Haskell possible. Thank you.
All right, thanks. So next up, I'm going to play a couple of videos from people who weren't able to make it today.
Hello everyone, I'm Suganya Raju. I'm going to present on structured errors and error codes in Cabal install, which I'm working on as part of Summer of Haskell under the mentorship of Gershom Beserman. Unfortunately, I couldn't attend this event in person, but I'm glad to have this talk virtually. To begin with, I would like to start with the motivation behind this work. The Haskell error index describes various messages that can be returned by Haskell-related tools, including both errors and warnings. For example, GHC started emitting a code with the format GHC followed by a unique numeric code for its error messages starting from version 9.6.1. So far, 102 errors and warnings are documented here. These codes can be looked up in the Haskell error index site for further information. Such a centralized error index works better when more Haskell tools participate. So the aim of this project is to integrate errors in Cabal install with the error index so that they can be centralized and documented as well. In the same vein as GHC and Stack, this project is to refactor the Cabal code base to provide structured errors rather than mere strings. So why is there a need for structured errors? An oft-repeated challenge in learning Haskell is the quality of error messages, especially for beginners like me. For example, an error message may have an unknown provenance, whether is it generated by Stack or by Cabal or by GHC or by Haddock. An error message may mention concepts unfamiliar to the programmer or unrelated to the problem. Sometimes they contain too little information. These kinds of problems can be solved by having structured errors. For example, if a programmer runs into an error and the error message is prefixed with a code in the format Cabal followed by a numeric code, it can be easily understood that the error is in the Cabal tool, and the numeric code can be looked up in the index to understand better. Thus, it helps in categorizing the errors into its respective Haskell tool, and new users don't have to figure out which tool is the source of the error. And this will eventually lead the users to have an easier time contributing documentation for how to work around various situations that may arise. So what will be the outcome of this project? The idea of the project is to have one data constructor per error and create a data type for exceptions that have specific constructors for each one and is incrementally added to. Along with this, there is a display instance that turns it into a string to emit and an associated numeric code for each constructor. Then at the top level, the handler that catches and emits exceptions will format the numeric code and the string all at once. So our end goal is to have a package-specific error data types where each constructor of such a data type will represent one error corresponding to the error that the module can throw. With respect to the existing error infrastructure, currently Cabal usually terminates with an error through calling the die-dash function. This die-dash function takes a verbosity, an error string, and throws an exception that just wraps up the error string, and the call stack information is already rendered within it. In order to have structured errors, there are a few core changes we have done to the existing infrastructure. The first one is the introduction of two new sum types. One for Cabal package, that is Cabal exception, and the other for Cabal install package, which is going to be Cabal install exception. Second change is a creation of one more data type named verbose exception, which will be a wrapper for data types Cabal exception and Cabal install exception, and it will also capture the call stack and the verbosity. The third is an introduction of a new function, die with exception, which will be polymorphic over exception types and will replace the die-dash function in all of its occurrences in the Cabal code base. And this is how it looks when the exception is instantiated. Each error message is assigned a unique code of the form Cabal, followed by a unique numeric code, and rendered along with the metadata at the display time of exception. Here, I have taken a small part of the module in the Cabal package to reference. As you can see the difference in the proposed design, the die-dash function is replaced with the function die with exception, which takes in the verbosity and the exception it is supposed to throw. After this, the exception is caught and pattern matched to retrieve the error code and the error message accordingly. So once this executes, this is how the new error output with the error code is going to look like. As you can see, there is error followed by the cabal and the numeric code. This is a screenshot of the Haskell error index, which has errors from GHC and stack for now. The error code that we have generated as part of this project will be added to the existing error index, just like the way it is shown here. Once this is done, users will be able to read about why an error occurs and the cause for the same. And that's the end of my talk. Thanks to my mentor, Gresham Baserman, and the Haskell community for their support, guidance, and this opportunity. Thank you. I'm going
Hello,
to
everyone.
present on errors and error codes
I'm
in
one of the
Cabal
students.
Inst.
Hello, everyone. My name is Nathan Maxon, and I'm one of the students for this year's Haskell Summer of Code. So let me introduce myself. I started programming when I was young. I started with PHP. Later I did some Python, some Java, and then learned a bit about Scala and Haskell. However, for university, I studied teaching Chinese to foreigners. Later, I worked teaching English and translating. Eventually, though, I decided I would like to go back to programming for a living. So, toward that end, I applied to this year's Summer of Haskell. Disclaimer about this project. What I was working on was the interaction between the HLS server and the LSP client. So there were no significant user-facing parts to this project, so that means no screenshots or fancy videos. So let me give you a little bit of a background behind the project. The first work to support Resolve was done by Zubin Dugal from Well-Typed, and he added Resolve to completion items, or support for completion items / Resolve to HLS, and this allowed him to delay the computation of the documentation and types field for completion items and provided significant performance improvements. But my project was to follow up on his project and add Resolve for code actions and code lenses, as well as to go and make Resolve easier for plugins to use. So let's talk a little bit about what Resolve is. For those who don't know, LSP is Language Server Protocol. It defines specific methods that allow the client, like Emacs or VS Code, to request information about a code file from the server, in this case, HLS. One method, for example, is called text document / code lens. It's a request to return a list of code lenses for the whole document. If we're not using Resolve, we need to compute the title and return that along with a range for each lens. However, when we are using Resolve, we can instead just return a range for each code lens. And when they come into view, the client will send us a request for the title. This allows us to delay the computation of the title. So Resolve is not just for code lenses. We have Resolve for code lenses, for completion items, for code actions, among many other methods. But what we can resolve for each method is different. So code lenses allow us to go and resolve the title. Code actions allow us to resolve the edit. Completion items allow us to resolve the documentation fields. So let me give you a little bit of an overview of what my project entailed. For those of you who don't know, previously LSP types, the package was handwritten, and because of that, it would always lag features compared to the latest LSP spec. But Michael made a new version of the LSP types package, which was generated. So we had all of the types from the LSP spec, and we could always stay up to date. The only problem was that this wasn't implemented in HLS yet. The new package wasn't supported in HLS yet. So this was my first part of the project. It was intense, but it was also educative, as I had to go over every part of HLS. Many of the changes were small, and for those, Haskell's easy refactoring really came into play, as most of the time I could follow the types and see where that led. There were a few tricky problems. There were some bugs in the LSP types package because HLS was the first user of the new version, and those bugs I had to fix. But in the end, I made up about 5,000 changes, and it touched around 194 files. So after that, I ended up implementing Resolve in HLS itself. A naive implementation of Resolve methods in HLS is pretty simple because HLS doesn't really need to know very much about the methods that the LSP client sends. But in addition to general support, I also added some quality of life improvements, allowing plugins to have an easier life supporting Resolve. So one example of that quality of life improvement is that we automatically deserialize the generic JSON data field that we get to the handler specified argument type. So we'll talk a little bit more about that later. And for some of the methods, they only supported Resolve relatively recently, for example, for code actions. And we still want to support older clients that don't support Resolve. And where one option would be have every plugin check what the client supports and then change your behavior depending on that, we instead opted to go with a method where we actually dynamically rewrite the plugin's response depending on whether the client actually supports Resolve or not. And that allows the plugin to go and be completely ignorant of whether the client supports Resolve or not, and allow it to have a lot less code and more cleaner code. I also implemented Resolve in 7 plugins. Part of that was understanding what would be the best way to implement Resolve in HLS. Along the way, I also fixed several bugs. So some of the bugs I fixed, preventing an exception in commands from taking down the whole server. Commands are the type of request that we get in HLS. I fixed a Pragma plugin from offering incorrect code actions for HLS diagnostics. I fixed explicit record fields from offering duplicate code actions when inside a HS expanded clause, which is like what we use for new JC features. And sorry, one second. And I also merged the explicit imports and refined imports plugin that ended up removing a lot of duplicated code. I was also able to work on some HLS projects that weren't strictly related to my main Haskell Summer of Code project. So one of them was making a significant improvement in the GHCID code base and allowing us to have much cleaner code base and moving towards where we can turn on WArr for GHCID. We already turn on WArr for GHCID, but we have to make certain exceptions. So we have to cut down significantly on the amount of exceptions we had to make, and I left behind a much cleaner code base. The next thing I did was actually building off another member of the Haskell language servers, Fender's work. He had started, but he didn't have time to finish, so I took up his project and I did some changes to it. The project was changing how plugins handle errors, a rather large change to how plugins handle errors. And previously, every plugin would respond with a LSP response error, but that didn't work very well because there's no easy way to combine them. But we came up with a consistent way that plugins could have specific plugin-specific errors that they could respond with. And all plugin responses are now crafted in the ICFP monad, which allows us to throw errors and short-circuit the rest of the code easily. In addition, we have a bunch of commonly used functions that also throw the right error if they fail, which is, we have good failures and we have bad failures, and this allows us to know exactly what's happening inside a plugin. So let's go and take a look at what Resolve looks like in HLS right now. This is an actionable example of Resolve in the HLN plugin. So let's start with the type, resolve function, ID, state, HLN resolve commands, method, code action, resolve. This is a type synonym because the actual type is quite long. So it's a function that takes ID, state, plugin ID, code action, URI, HLN resolve command, and is executed in the ICFP monad. So a lot of these are actually pretty standard for all resolve handlers. ID state is, plugin ID is, code action would be considered the parameters for the request. The URI is helpful because we always need the URI when you do pretty much anything in HLS. HLN resolve command is what we extract from the code actions data field, and we deserialize it for this resolve handler. And if you're unable to deserialize the data field to HLN resolve command, then we won't call this resolve handler. So if you remember from before, every request has different parts of different fields rather that can be resolved. And for code actions, we can resolve the edit field. So here we're returning the code action with the edit field replaced with the edit that we computed. I would like to especially thank my mentor, Michael, for his guidance through my project. He was awesome. In addition, I'd like to thank the Haskell Foundation and all Haskell Summer of Code sponsors for providing me this opportunity to spend the summer improving HLS. Thank you all.
We're going to swap the computers now.
Hello? Okay. All right. Working? Showing my screen. All right. hope I'm audible. Yeah. So, good afternoon. I'm Sachi, and I've worked on a project called Tidal and Mandalas, and I've done it under the researcher Alex McLean at Then Try This. Correct. So, some background. I was in a women engineers program in India, and that's where I was introduced to Haskell around 2 years ago. But I did not start taking it seriously up until December of last year, wherein I did a project in it, one of my first bigger projects. So that was called PAIP Goes Haskell. Paradigms of Artificial Intelligence Programming is a book by Peter Norvig. It's about classical AI programs from before the 90s, so about programs pre-neural networks essentially. And the programs in it are written in Lisp, and we converted it into Haskell and Golang. I specifically worked on the Haskell part. And I learned a lot here, but I wanted to do larger projects. So I saw that Summer of Haskell was accepting applications and beginners were encouraged. And additionally, I saw that in my project, last year the contributor was also an Indian student, so that encouraged me a lot. So this is my project. My proposal was to produce beautiful visualizations in Tidal Cycles, the platform for live coding, using, to produce mandala visualizations. What are mandalas? They are repeated geometric patterns formed by circles, squares, and these combine in specific manners to produce these visualizations. They are fairly common in Southeast Asian art, and but they are generalized to an extent that they can be used in many different places and are fairly common now. So what is Tidal Cycles? Tidal Cycles is a live coding environment for producing music, and it has a mini notation that is essentially a DSL built on top of Haskell. So you take snippets of music, like suppose BD over there is a bass drum, a snare drum, and then you apply functions on it. You compose these functions to produce music. So I'll just show an example. Will it load? Yeah. This is a clip of somebody producing music. It's not audible, is it? Great. Fantastic. But is it? Yeah, I need to connect this. All right. Still not working? All right, great. I'm going to try to play this.
This is connected.
This?
Yeah, it's this.
Yeah.
This is connected. Sorry about that.
Okay, this is not. Yeah, it's not. Okay, it's all right. I'll just continue. We can show this later also. Right. So it produces music with functions. The problem, as you could see, were visualizations. If you saw the first clip, they were just notes moving forward with time, nothing special. So I thought that since all these functions will work on underlying structures, those can be used to make mandala-like patterns. So initially, I thought, okay, let's go to the basics. I thought about when I was in 6th grade, I used Microsoft Visual Logo to make circles and squares, and I thought, okay, we can use that. So a logo-like system to produce graphics, and basic notation, move forward, move right, move left. And the library I used was World Turtle, which is built on top of Gloss. This is an overall overview of my approach, but it's a basic approach. Initially, I tried to explore Tidal, saw what functions it had. Then for a while, I explored what animation libraries I could use. And additionally, I also did some more research on mandalas. I created a basic turtle notation in Haskell. And after that, I integrated that with Tidal's parser in order to produce the turtle notation values. And I also integrated it with World Turtle to produce the turtle notations can produce the animations. But there was a problem. My system's not real time. So I was taking a pattern and I was just querying it for like, okay, 400 seconds, give me all the values. But at a particular point in time, I did not know what value to take. So I went a level lower to gloss and tried to explore whether this would be possible. And that's where I am at right now. I'm working on that. So let's do a demo. All right. So I would first like to go bigger. Yeah, 1. So if we look at some basic patterns, for example, let's go forward. It goes forward, great. But if we go, okay, that's making a square. What's that doing? That pattern goes F and then R. So in the first half of the cycle, it goes forward, and in the second half of the cycle, it goes by a factor of 90 to the right. And this is proportional to the time in which the pattern is active. That's over there. So the first half, it goes forward, second half, it goes right. This is proportional to the time. All right, let's try something else. All right, we're getting different shapes over here. That's working, that's doing something else different because the time for which the pattern is active changes. All right. Okay, so now we'll go to some mini notation stuff. So these are different ways in which the mini notation manipulates the pattern. So, okay, it goes forward, goes left, right, forward, forever. Not forever, for the cycles. And at this point, we start seeing some interesting things. This is making a spiral sort of structure. And yeah, it'll go on for a while, but that's what it's doing. All right, and finally, but this is just manipulation with the mini notation. The title has additional functions also. So yeah, these are just 2 of the functions, fast and slow. Fast speedens a pattern, and slow slows it down. So if you go for the first one, okay, that's the second one is doing. But you can slow it down by a particular pattern also. So the value it is using, this is producing the second one, is slowing it down by the Fibonacci series till like 1 through 8. And as you can see, it's doing something very strange. I don't know what that is either. So these are some of the patterns that I have produced. This pattern produces this weird spiral looking thing. We have this festival called Diwali where we make rangolis on the ground. They look kind of like this. I like to call this one a ninja star with like some clan that it's really hot in their area, so they need a fan. And this one is what that pattern is. So it goes in all these different weird directions and comes back to its original spot. And I think it's symmetric along some axis, but I'm not entirely sure which one. And my friend who likes physics told me it looks like Brownian motion, and I was just thrilled by that. So yeah, what are my learnings from this project? The 2 main ones are thinking in different programming paradigms. So I love working with Haskell. I think it's a beautiful language, and it allows me to think differently at a different level of abstraction. And additionally, I saw how different fields were interconnected visually. Like I was able to see that rather than just abstractly think about it. So obviously these musical patterns producing different kinds of patterns. And yeah, even the comment about Brownian motion, like I just thought it was beautiful to see that. So finally, the future scope of this project includes, Tidal has a new version coming out, so I want to integrate with that version. Additionally, I saw that L systems can be produced using Turtle graphics, and I wanted to see if these can be produced with this framework. There's a problem because Tidal doesn't really use state that well, but we'll figure it out. And I have to deploy my project on Hackage. So again, these are the links to the repository. Thank you to the Haskell Foundation, haskell.org, for sponsoring this project. It's been a great time, and my mentor, obviously, Alex McLean, for mentoring me through these months. Thank you.
Or presenter waiting on Zoom. Can we switch to Zoom?
Hi, I'm Elodie Lander, and I have been working on getting go-to definition in Haskell language server to work for external dependencies in a project. So I'm going to start with a live demonstration. So let me just share my screen. And okay, can you all see everything here? Okay, so can you see the launched VS Code here? Yes. Okay, great. All right, so here is a function that is not part of the project. And so I was able to go to definition. Once I have a dependency file open, hover works, and go to definition also works in here. Let's go to a different one. Let's go to the ASON. Yeah. And so then from here, I can go to another definition. And I can even go to transitive dependencies. That's not going to work. But we go back to this. And so we can go to internal dependencies. And so let's talk about a little bit how is this working. So you can see up here the file that is open right now. So we're putting this in a .hls directory inside of the project. So you have my sincerest apologies that if you're using Haskell language server and you start using this feature, you're going to have to add .hls to your gitignore. We talked about the possibility of opening these dependencies where they are. The Rust community is able to do this, but the way that they do it is just through the client, through VS Code. And we decided that that was interfering too much with how the language server protocol is intended to be, and we didn't want to do that, especially because we have support for multiple different clients. So we're opting for this, where we put inside HLS dependencies, and then this is essentially going to be the same name of the directory that you would see in the Cabal store. And then we have the Haskell file. So how does this work? So the first thing that we need for this to work is we need Cabal head. So the first thing that I did in this project is, how do I move this? Oh, there we go. Is I made a small change to Cabal that allows it to copy HIE files into the Cabal store if the user has the fwrite IDE info GHC tag enabled in their Cabal configuration. So the most important line of code in this change is where we actually set the HIE dir flag. So this, oh, it's right here. Okay. So the HIE dir flag, this changes where HIE files get produced when the FRI IDE info flag is enabled. So what we opted for in this is to put it in a directory called extra compilation artifacts. This is a directory that Cabal was already producing for GHC plugins, and it already copies this directory when it's installing a package in the Cabal store, if it exists. So basically just adding this directory in was the main thing that needed to happen for this change. So let me show you. Okay, so we're looking at dependent map, and this is that. So let's take a look at what the Cabal store looks like. So we've got dependent map, and this is 0.4.0.0 dash, and this is D. Yeah, okay, so if we look in here and in the lib directory, there's the extra compilation artifacts directory. And if we do tree on that, you can basically see this is the whole dependent map package, but with just HIE files instead of HS files. So this is what Cabal now produces, and this is what Haskell Language Server can now look for. So now let's take a look at the main pull requests in Haskell Language Server. So there's two main components to what makes this possible. So the first thing is, let's take a step back and talk a little bit about how go-to definition worked before. So essentially, Haskell Language Server, when you go to a definition, it's gonna grab the name of what you are going to, essentially from the HIE AST that it has. And then it's gonna try and load that up. And if it can't find it in its own environment, then it's gonna look in the HIE database. So there's a project called HIEDB, which is maintained by my mentor for this, Zubin Dougal. And HIEDB essentially is an SQLite database that has it has tables for the modules in a project, for example, and the units, the packages. And so the lookup, the go-to definition code, when I came to it, was designed in such a way that it was intended that we would have go-to definition support for external dependencies at some point. So basically, I just needed to fill in the definition of lookup mod. You can see before the changes, it was a stub that was just returning nothing. But basically what this does is this file path here is an HIE file that we got from the database. So this is assuming that we already have indexed in the database all the HIE files that we need. And this is going to load up the HIE file, and basically all it does is get the raw byte string of the Haskell source from the HIE data type and write it out in the HLS/dependencies directory. There's a few more things that this does in terms of the database. So when we initially index an HIE file, we're not gonna have the source file in the database, in the SQLite database, because it doesn't exist yet. But when we actually get to this point where we have the HIE file, at this point we are going to register the Haskell source file that's in .hls/dependencies in the database. And that's the behavior that you just saw in Visual Studio Code. All of these are dependencies that I've brought up before. So this was essentially just looking, it never actually even made it to this code, right? It was just saying, oh, that Haskell source is in the database and we can just bring it up and that file already existed, I'm pretty sure. So the other main component of this functionality is in a new file, which is called, core dependencies. And this is where all the indexing happens. So this grabs data from GHC. So there's a data type in the GHC API called an HSC-env. And that has all kinds of information about what packages are available to the compiler as it's building our libraries. So the main function here is index dependency HIE files. And this gets called every time a new HSC-env gets loaded up by Haskell Language Server. So essentially what we're doing here is we're grabbing all the dependencies from the HSC-env. We're filtering them using this function, calculate transitive dependencies, to make sure that we're only getting things that are dependencies and transitive dependencies. And then we are sending them off to the function that already existed for indexing an HIE file in the HIEDB database. So that function, well, I don't think I need to get too into details about how that works, but so all of this stuff gets put into the database. And then once we call go to definition, then it's just, if the Haskell source file has not been written out yet, then we can just look in the database and it should be there. And then we can write out the file and open it up in the editor. So what are the limitations of this? So the first thing is you need to have a recent enough version of Cabal installed. And we don't currently have support for libraries that are bundled with GHC to be indexed. So let's take a look at that. This is a patch that is to be merged in GHC, specifically in the Hadrian build system, that will basically mimic the functionality of what we did in Cabal, where we're going to have an extra compilation artifacts directory with all of the HIE files. And we're going to enable FWrite IDE info so that GHC is going to produce the HIE files for all of those directories. So as an example, currently, if I try and go to the definition of just, for example, just is defined in base. It's packaged with GHC, so we don't currently have the support for that, right? This is going to need a little bit more work still also because, so this will make the HIE files in a subdirectory of the build directory, the Hadrian build directory, called libraries. And what actually gets put into a binary distribution is another subdirectory called lib. And I believe at this point that cabal copy is what moves currently HI files and like dyn HI files from the libraries directory to the lib directory. So I think there's one more change that will need to be made in cabal to get this to essentially package up the HIE files that for all of the packages that go with GHC in much the same way that cabal will be installing them in the cabal store. Another thing that there's another potential pitfall that users could run into where so say you've been working with Haskell Language Server with an older version of Cabal, and then you get the latest code and you want to try out go-to-definition for a dependency. And so you upgrade your Cabal, but say you already had FRI IDE info enabled. So the hash that goes into the Cabal store directory and also the HLS dependencies directory, that, as I understand it, includes all of the GHC flags, but it does not include the version of Cabal that you used. So it's possible that you could have built your dependency with the FRI IDE info flag, but an older version of Cabal, and so you have the same hash here in the directory, but you don't have the HIE files. So in this case, I still need to make an error that will give the user a warning that says, hey, it looks like you are missing some HIE files that we're expecting to find, and suggest that they maybe nuke their Cabal store and rebuild everything. So the Cabal pull request was merged a couple months ago. Still working on getting the Haskell Language Server PR merged. I'm expecting that will happen in the next couple of weeks. And same thing with the GHC patch. So I think that's about it. Does anyone have any questions? Oh, I'd just like to thank everyone who has commented on my PRs and given feedback, and of course, my mentor, Zubin, who has brought a real depth of knowledge from both Haskell Language Server and GHC to help point me in the right direction at a bunch of different junctures in this. So, and thank you to the Haskell.org committee for sponsoring this project.
All right, thank you. All right, that's everybody. And thanks to the contributors. That was fantastic. And looking forward to next year.
Thank you very much. I don't know if you have any questions about to Aaron, I guess. No. Okay. Nice. Okay, so it will be fast. So this is the end of Haskell Symposium. Thank you all for attending. I want to thank specifically Well-Typed that sponsor the Haskell Symposium, and I want to thank the speakers and attendees. I want to thank our two keynote speakers that I really enjoyed. My co-chair, Trevor, the steering committee, the organizers like Nikhil Swami, who is the general chair, and Yannick Foster, who was the workshop chairs, and all the student volunteers who helped us very, very much. I want to thank the program committee, which was a very nice committee where Facundo is here, and Leo and Netsko, who were around here and also chaired the sessions. Okay, let me tell you very few things about the submission process. What we changed this year compared to the previous one, we didn't have an abstract deadline. That was there last year. And what we tried to do this year, we tried to have this artifact submission. And the idea was to submit artifact at the same time that you submit the paper, so the reviewer can also check the artifact. And then we didn't do another round of artifact submission, which I think is like what most conferences do, to submit all the material together. And the paper categories were the standard, the same as the previous time. And the review process was lightweight, double-blind. So the paper statistics, we had only 15 submissions. So 12 regular papers, 1 demo, 1 experience report, 1 functional Perl. We had 3 reviews per paper, and we accepted, So we accepted 8 papers. We accepted the Perl, the experience report, and then from the 12 papers, we accepted 6, which give us like 53% acceptance rate. And then we accepted demo, and we made like, for 3 papers, we suggested them to come as a demo because we thought that the topic was very nice, but the writing was not so good to go in the proceedings. Okay, that is what happened. So some thoughts. The number of submissions was low. It was 15 this year. Last year it was 20. And the before COVID era was 30, more or less. And we have been thinking of some ways to improve, to increase the number of submissions. And one way that I think it could work is, instead of have full papers, to have these 2-page abstract submissions. So like in the next year, check, because I really hope we will be able to do that. And another idea that we have been thinking is if we see Haskell Symposium as a way to start the submission of a GFP paper. But for both of these, we are thinking about them. Nothing is certain yet, yes.
So with those 2-page abstract submissions, they still peer reviewed and make it into the proceedings?
No, the 2-page abstract submission will not make it into the proceedings. Is like what I am thinking.
Because if you do that, then students may have a hard time getting funding to come.
Yeah, I think this is a good point that I didn't know about, because as I said before, like we received 3 papers, we didn't reject them. We told them come present it as a demo, and 2 of them didn't come because they couldn't find funding. Yes. But I don't know if, I don't know. For me, the proceedings is something that should satisfy some writing requirements. We could also think about getting some sponsorship for students to come. But yeah, we have a steering committee to discuss all this. But there are many ideas, so you can tell me any ideas, or you can tell more ideas to our next year's chair, who is going to be Garrett Morris. And with this, I want to thank Garrett and all of you who are attending. Thank you.